Hey everyone, today's journey leaves the cradle of our solar system and carries you 600 light-years away to the enigmatic shores of Kepler-22b as we explore why Kepler-22b could shape humanity's future. Before we begin, please leave a like and subscribe if you haven't already. Your support fuels these voyage of discovery stories. Let us know where you're tuning in from and what time it is. We love learning about our cosmic crew. Now settle in. Imagine standing beneath a distant yellow star filtered through an alien atmosphere, and brace yourself for crushing pressure, swirling clouds of exotic gases, and temperatures that flirt with the boiling point of water. Prepare to feel gravity stronger than Earth underfoot, hear the distant pulse of stellar radiation, and witness a world that could redefine the future of human life. The discovery of Kepler-22b begins with the peculiar, almost imperceptible dimming of a star. Not just any star, but one remarkably similar to our own Sun, located 620 light-years away in the constellation Cygnus. As you watch the data streams flowing across the monitoring screens at NASA's Ames Research Center in California, your eyes might miss it entirely. A fractional dip in brightness, occurring with clock-like precision every 290 days. The star is Kepler-22, and that minuscule shadow passing across its face represents something humanity has been searching for since we first gazed skyward, a potentially habitable world beyond our solar system. The year is 2011. The Kepler Space Telescope has been silently orbiting the Sun for nearly 3 years, its unblinking eye fixed on a single patch of sky containing more than 150,000 stars. Your fingertips tingle as you scroll through the endless stream of light curves, the graphical representation of each star's brightness over time. The room around you hums with the soft whir of computer fans and the occasional murmur of scientists. The air carries the faint scent of coffee gone cold and the sterile coolness of climate-controlled laboratory spaces. Data from the Kepler mission arrives in waves, overwhelming in its volume. To comprehend the scale, imagine yourself standing on a beach, tasked with identifying a specific grain of sand among millions. Each dip in starlight could be meaningless noise, a sunspot, an instrument glitch, or the shadow of an undiscovered world. The algorithms flag thousands of potential signals, but human eyes must verify each one. Your vision blurs after hours of examination, the fluorescent lights overhead casting a pallid glow across your skin. Then there it is. The pattern emerges. 3 distinct transits of an object across Kepler-22, spaced almost exactly 290 days apart. The regularity speaks of orbital mechanics, the predictable dance of a planet around its star. Each transit dims the star's light by just 0.00029%. Through the transit method, which measures a planet's size by tracking how much starlight it blocks, astronomers calculate that this object must be approximately 2.4 times the size of Earth. The significance washes over you in waves. This is not merely another exoplanet to add to the growing catalogue. What sets Kepler-22b apart, sending a chill down your spine despite the warmth of the room, is its orbit. At a distance of 0.85 astronomical units from its star, equivalent to roughly 79 million miles, Kepler-22b sits squarely within the habitable zone, the region where temperatures might allow liquid water to exist on a planetary surface. Can you feel the weight of that knowledge? A potentially Earth-like world, circling a Sun-like star, at just the right distance for the chemistry of life, as we know it, to potentially flourish. Your heart rate quickens as you consider the implications. The monitors around you continue their steady display of cosmic data, but now they seem somehow different, as if the universe has just whispered one of its secrets directly to you. The confirmation process stretches over months. Multiple telescopes train their focus on this distant system. Ground-based observatories in Hawaii, Chile, and Spain collect additional data. The Keck Observatory on Mauna Kea uses its adaptive optics to pierce through Earth's atmospheric distortion, searching for any false positive signals that might explain the transit data. None are found. The Spitzer Space Telescope, operating in infrared wavelengths, confirms the transits from its vantage point above Earth's atmosphere. In the verification room, tension builds with each new data set. You can almost taste the metallic edge of anticipation as scientists pore over the numbers. The calculations are run and rerun, examined from every possible angle. Statistical analyses determine a false positive probability of less than 1 in 10,000. The conclusion becomes inescapable: the signal is real. Kepler-22b exists. The first measurements tell us the basics. Kepler-22b completes an orbit around its star every 290 days, slightly faster than Earth's 365-day journey around our Sun. Its star Kepler-22 is a G-type main sequence star like our Sun, but slightly smaller and cooler, with a surface temperature of approximately 9,025 degrees Fahrenheit compared to our Sun's 9,940 degrees. This means that despite being closer to its star than Earth is to the Sun, Kepler-22b receives roughly the same amount of stellar energy that Earth does. The size measurements indicate a radius 2.4 times that of Earth, placing it in a category that astronomers call super-Earths or mini-Neptunes. These planets, common throughout our galaxy but absent from our solar system, exist in the mass range between terrestrial worlds like Earth and ice giants like Neptune. The exact nature of these intermediate planets remains one of the most compelling mysteries in exoplanet science. What makes your palms sweat as you process this information is not just what we know, but what remains unknown. The Kepler telescope can determine the planet's size and orbit with remarkable precision, but it cannot tell us its mass or composition. Without this crucial information, Kepler-22b could be a rocky world with mountains and valleys, an ocean planet covered entirely in water, or a gaseous body with no solid surface at all. The difference is not merely academic. It represents the boundary between a potential second Earth and just another inhospitable world among billions. The search for additional data intensifies. Astronomers attempt to measure the gravitational wobble that Kepler-22b induces in its star, a technique called the radial velocity method. This would reveal the planet's mass, allowing scientists to calculate its density and infer its composition. But the measurements prove challenging. Kepler-22 is too dim, and the signal too faint, for the instruments available in 2011 and 2012 to make a definitive determination. The best estimates place an upper limit on Kepler-22b's mass at approximately 36 times that of Earth. If the planet were to have this maximum mass and the measured radius, its average density would resemble that of the gas giants in our solar system. But the true value could be much lower, potentially allowing for a predominantly rocky composition more similar to Earth's. As the announcement date approaches in December 2011, you feel the peculiar mixture of excitement and scientific caution that characterizes major astronomical discoveries. In the conference room, the projected images of light curves and orbital diagrams cast a blue glow over the faces of researchers. The air feels charged as if before a thunderstorm. Someone adjusts the thermostat, but the chill you feel comes not from the room's temperature but from the vastness of the implications. The official announcement on December 5, 2011 sends ripples through the scientific community and beyond. Headlines proclaim the discovery of an Earth-like planet in a habitable zone. Images appear in newspapers and websites worldwide, though none are actual photographs of Kepler-22b. Instead, they are artistic renderings, educated guesses based on the limited data available. Some depict a blue marble streaked with white clouds and continents. Others show a water world with no land in sight. The truth remains hidden by 620 light-years of interstellar space. In the days following the announcement, you find yourself standing at the window of the research facility, looking up at the night sky. Somewhere in the constellation Cygnus, too faint to see with the naked eye, lies Kepler-22. The star looks no different from countless others, yet now it carries special significance. Around it orbits a world that for the first time meets all the basic criteria scientists have established for potential habitability. The discovery of Kepler-22b occurs at a pivotal moment in exoplanet science. The first confirmed exoplanet, orbiting a Sun-like star, 51 Pegasi b, had been discovered just 16 years earlier in 1995. That world, a hot Jupiter orbiting perilously close to its star, shattered expectations about planetary system architecture. Since then, astronomers had detected hundreds of planets, most of them gas giants or worlds orbiting too close or too far from their stars to be considered habitable. Kepler-22b represents something different. It is the first confirmed planet of roughly Earth-like size orbiting within the habitable zone of a Sun-like star. Its discovery shifts the focus of exoplanet research from simply finding planets to characterizing potentially habitable worlds. You can feel this shift in the questions being asked in research meetings, in the grant proposals being written, in the instruments being designed for future telescopes. The limitations of current technology become frustratingly apparent as scientists attempt to learn more about this tantalizing world. The Kepler telescope, for all its revolutionary capabilities in finding exoplanets, cannot directly image them or analyze their atmospheres. Ground-based telescopes struggle to extract additional information from the faint signal of such a distant system. The planet's proximity to its star makes direct imaging impossible with existing instruments. These technological constraints lead to a peculiar scientific limbo. Kepler-22b exists in a state of both known and unknown. Its orbit and size are measured with reasonable precision, but almost everything else about it remains speculative. Does it have an atmosphere? What is its surface like? Does liquid water flow there? Could it harbor life? The answers lie encrypted in spectroscopic signals too subtle for our current instruments to decode. This uncertainty creates a vacuum that imagination rushes to fill. Scientific papers propose various models of what Kepler-22b might be like, exploring different compositions and atmospheric conditions. These models produce a range of possible scenarios: a rocky super-Earth with a thin atmosphere, a water world with global oceans hundreds of miles deep, a mini Neptune with a thick hydrogen-helium envelope surrounding a solid core. As you read through these papers in the quiet of the research library, the black and white diagrams and graphs seem to pulse with potential. Each represents a possible reality for this distant world. The paper between your fingers feels crisp and tangible, in stark contrast to the nebulous nature of our knowledge about Kepler-22b. The pages rustle as you turn them, a sound that seems louder in the contemplative silence. The discovery catalyzes new questions about our place in the cosmos. If potentially habitable worlds exist around stars like our Sun, how common might they be in our galaxy? What fraction of those worlds might actually harbor life? How many civilizations could be out there, perhaps looking back at our Sun and wondering the same things about us? The implications spiral outward, touching on astronomy, biology, chemistry, philosophy, and the fundamental question of our cosmic significance. Follow-up observations continue in the months and years after the initial discovery. Each new data point narrows the range of possibilities slightly, though definitive answers remain elusive. The James Webb Space Telescope, under construction at the time, promises to revolutionize the study of exoplanet atmospheres, potentially revealing the composition of Kepler-22b's outer layers. But its launch lies years in the future. In the meantime, other promising candidates emerge from the Kepler data: Kepler-62e and Kepler-62f, Kepler-186f, Kepler-452b, each one adding to the growing census of potentially habitable worlds. Some orbit closer to their stars, others farther away. Some are nearly Earth-sized, others substantially larger. But Kepler-22b retains its significance as the first confirmed exoplanet that checks all the basic habitability boxes. The narrative of Kepler-22b becomes part of a larger story unfolding across multiple research institutions and countries. The search for life beyond Earth no longer belongs solely to the domain of science fiction. It has become a legitimate scientific endeavor with dedicated instruments, methodologies, and funding. As you walk through the corridors of the research center, you notice how the posters on the walls have changed. Images of hypothetical exoplanets now hang alongside the familiar planets of our solar system. The universe has expanded in our consciousness. What makes your breath catch when you think about Kepler-22b is not just what we know about this specific world, but what it represents: the beginning of an era in which potentially habitable planets are not rare, mysterious objects, but catalogued, studied, and eventually understood in detail. An era in which the question of life beyond Earth might finally receive a data-driven answer. As the sun sets outside the observatory window, casting long shadows across the room, you find yourself contemplating distances both physical and temporal. 620 light-years represents not just a spatial gulf but a temporal one. The light from Kepler-22 that reaches our telescopes today began its journey 620 years ago, around the year 1400 on Earth. If we were to somehow send a message to any hypothetical inhabitants of that distant world, announcing our discovery of their existence, that message would not arrive until the year 2631. Yet, despite these vast distances, Kepler-22b feels surprisingly immediate in its impact on science and human thinking. The raw data may consist of nothing more than slight dips in the brightness of a distant star, but the implications press upon us with the weight of worlds. The air in the research facility seems to vibrate with possibility as scientists discuss the next steps in characterizing this enigmatic planet. As night falls completely and the stars emerge, your thoughts turn to the next challenges. What does Kepler-22b's atmosphere consist of? How does its star's radiation affect its surface conditions? What might gravity be like on a world potentially twice as massive as Earth? The questions proliferate, each one leading to another, creating a roadmap for future research. The mystery of Kepler-22b beckons, a siren call from beyond our solar system, inviting us to look deeper, build better instruments, and continue the search for answers among the stars. The habitable zone around a star exists as a region of delicate balance, neither too hot nor too cold, where water might persist in its liquid form. As you stand in the climate modeling laboratory, surrounded by screens displaying simulations of Kepler-22b's orbital dynamics, this abstract concept takes on tangible significance. The room temperature holds steady at 71 degrees Fahrenheit, maintained by systems that monitor and adjust with constant precision, much like the natural processes that might regulate conditions on this distant world. Kepler-22b orbits its star at a distance of 0.85 astronomical units, placing it closer to its Sun than Earth is to ours. In more familiar terms, that's approximately 79 million miles, a number so vast it seems abstract until you consider what it means for the planet's thermal environment. If Earth were suddenly transported to Kepler-22b's orbit around our own Sun, our oceans would begin to boil. Yet Kepler-22b likely remains temperate because its star, Kepler-22, emits approximately 25% less radiation than our Sun. The monitors around you display orbital simulations, the calculated flux of stellar radiation at different latitudes, and the predicted seasonal variations that would result from the planet's axial tilt, if it has one. These calculations contain uncertainty represented by error bars and confidence intervals that stretch across the screens like shadowy fingers of doubt. You can almost feel the heat differential as the simulations run, showing how Kepler-22b receives about 87% of the stellar energy that Earth receives from the Sun. What makes your pulse quicken is the realization that this places Kepler-22b well within the conservative habitable zone estimates. Unlike many exoplanets discovered in habitable zones that skirt the inner or outer boundaries, Kepler-22b occupies what astronomers sometimes call the Goldilocks region of its star's habitable zone, not just potentially habitable but optimally positioned. The star itself deserves close examination, as it shapes everything about its planetary companion. Kepler-22 is a G5-type star, slightly cooler and smaller than our G2-type Sun. Its surface temperature reaches approximately 9,025 degrees Fahrenheit compared to our Sun's 9,940. This temperature difference creates a distinct spectral signature, with Kepler-22 emitting slightly more of its energy in the red and infrared portions of the spectrum. Imagine standing on a hypothetical surface of Kepler-22b, looking up at its Sun. The light would appear subtly different from what we experience on Earth. Slightly more orange-tinted, the shadows perhaps a touch softer. Plants, if they existed there, might have evolved to capture different wavelengths of light, potentially giving them colors unfamiliar to human eyes. The sky itself might take on hues influenced by the star's spectral characteristics and the composition of the planet's atmosphere. The stellar type also determines longevity. GOV5 stars typically remain on the main sequence, the stable, hydrogen-fusing phase of stellar evolution, for around 15 billion years, considerably longer than our Sun's expected 10 billion-year lifespan. This extended period of stability provides more time for potential biological evolution, allowing complex life forms more opportunity to develop if conditions permit. The idea sends a shiver of possibility through you. What forms might life take given billions of years more evolutionary time than Earth has experienced? Stellar activity presents another crucial variable. Young stars often exhibit violent flaring and coronal mass ejections that can strip away planetary atmospheres and bathe surfaces in sterilizing radiation. The screens before you display measurements of Kepler-22's chromospheric activity, indicating a mature, relatively stable star. Spectroscopic analysis reveals calcium H and K emission lines consistent with a star of its age and type, suggesting activity levels similar to or slightly less than our Sun. This stellar stability matters enormously for habitability. A planet might orbit in the perfect zone for liquid water, but if its star bombards it with frequent high-energy flares, life could find it difficult to gain a foothold. The relatively calm nature of Kepler-22 adds another positive factor to the habitability equation. You can almost feel the steady, reliable warmth of this distant star as you consider the data, a cosmic hearth potentially nurturing a world we've only begun to understand. The habitable zone itself isn't static. As stars age, they gradually increase in luminosity, causing their habitable zones to migrate outward. Climate models running on the supercomputers down the hall from where you stand simulate these changes for Kepler-22b. The displays show timelines stretching billions of years into the future, with colored bands representing the moving boundaries of the habitable zone. Currently, Kepler-22b sits comfortably within this habitable region, but the models show how this might change. In approximately 2 billion years, Kepler-22 will brighten enough to push the inner edge of the habitable zone outward, potentially beginning a process of gradual warming on Kepler-22b. This slow-motion climate shift would unfold over billions of years, potentially giving any life that might exist there time to adapt or migrate. This temporal aspect of habitability adds yet another dimension to consider. A planet isn't simply habitable or uninhabitable. It exists in a state of ongoing change. You watch the simulations with a sense of cosmic perspective, aware that you're witnessing the potential life cycle of a world compressed into minutes on a screen. The room feels suddenly vast, as if the walls have dissolved to reveal the immensity of time and space being contemplated. The stability of Kepler-22b's orbit represents another critical factor. Subtle gravitational interactions with other planets in a system can dramatically affect orbital eccentricity, how elliptical rather than circular a planet's path around its star becomes. High eccentricity leads to extreme seasonal variations, as the planet moves significantly closer to and farther from its star during different parts of its year. Current data indicates that Kepler-22b maintains a nearly circular orbit, with an eccentricity close to zero. This orbital stability helps maintain relatively consistent stellar heating throughout its year, avoiding the extreme temperature fluctuations that would result from a more elliptical path. The steadiness of this orbit adds another point in favor of potential habitability, allowing for more predictable climate patterns. What about the length of Kepler-22b's day? The rotation period of the planet remains unknown, creating a significant uncertainty in climate models. A slowly rotating world would experience extreme temperature differences between day and night sides. A rapidly spinning planet would distribute heat more evenly, but might generate powerful storms in its atmosphere due to Coriolis effects. The simulations before you explore multiple possibilities, from a day similar to Earth's 24 hours to a tidally locked scenario where one side of the planet perpetually faces its star. Each rotation rate creates distinctly different climate patterns. In the tidal locking scenario, the screen shows a permanent hot spot on the day side and eternal night on the far side, with potentially habitable conditions only in the twilight boundary between them. The thought of such a world half-scorched, half-frozen, with life perhaps clinging to the narrow band between extremes, sends a chill across your skin despite the climate-controlled laboratory air. Tidal effects extend beyond rotation to influence other aspects of planetary evolution. The gravitational pull between a planet and its star can generate internal heating through tidal flexing, potentially maintaining a molten core and active geology long after a planet might otherwise have cooled. This internal heat drives the dynamo effect that generates magnetic fields, crucial for protecting any atmosphere from being stripped away by stellar wind. The instruments measuring Kepler-22b cannot yet detect whether it possesses a magnetic field. This represents one of many crucial unknowns that keep scientists awake at night, puzzling over probabilities and possibilities. A planet without magnetic protection in the habitable zone might still be uninhabitable, its atmosphere gradually eroded away by the constant stream of charged particles from its star. The star's radiation spectrum affects not just temperature but photochemistry, the complex reactions driven by light energy in a planetary atmosphere. Different wavelengths catalyze different reactions, creating and destroying molecular species that can dramatically alter climate. Ultraviolet radiation can break apart water molecules in the upper atmosphere, allowing hydrogen to escape to space and gradually dehydrating a world. The balance between water retention and loss depends partly on the star's ultraviolet output. Kepler-22, as a G5-type star, emits somewhat less ultraviolet radiation than our Sun. This potentially reduces the rate of atmospheric water loss on Kepler-22b, a favorable factor for long-term habitability. The monitors display spectral energy distributions as colorful graphs, with Kepler-22's ultraviolet output indicated by a lower curve compared to the solar reference. You find yourself reaching out unconsciously toward these displays, as if to feel the quality of this alien starlight on your skin. Stellar evolution models predict that Kepler-22 has been in its stable main sequence phase for approximately 5 billion years, similar to our Sun's current age. This suggests that Kepler-22b has experienced relatively consistent conditions for a span of time comparable to Earth's entire history, from the formation of the first simple cells to the emergence of complex life and eventually civilization. The implications hang in the air around you, unspoken but profound. If life follows similar trajectories elsewhere, what might 5 billion years of evolution produce on a world so tantalizingly Earth-like in its orbital characteristics? Beyond the average stellar flux, seasonal variations significantly impact habitability. If Kepler-22b has an axial tilt similar to Earth's 23.5 degrees, it would experience seasons as our planet does. However, its slightly shorter year of 290 days would compress these seasonal cycles. Winter would arrive more quickly, but also end sooner. Plants and animals, if they exist, would have evolved to synchronize their life cycles with this more rapid rhythm. The seasonal simulations on the screens show swirling atmospheric patterns shifting as Kepler-22b orbits its star. With each passing model day, you can almost feel the changing angle of sunlight, the gradual warming and cooling cycles that would define life on this distant world. The climate models incorporate dozens of variables, from cloud formation to oceanic circulation patterns, all dependent on assumptions about the planet's rotation, atmospheric composition, and surface features. One crucial consideration in these models is the greenhouse effect, the process by which certain gases in an atmosphere trap heat, warming the planet beyond what direct stellar radiation alone would accomplish. Earth's habitable temperature depends on a modest greenhouse effect from water vapor, carbon dioxide, and other gases. Too little, and our world would freeze too much, and it would overheat like Venus. Without knowing Kepler-22b's atmospheric composition, scientists must consider multiple greenhouse scenarios. The displays show several different projections, one with an Earth-like greenhouse effect maintaining average temperatures around 59 degrees Fahrenheit, another with a stronger greenhouse effect pushing temperatures toward 86 degrees, a third with a runaway greenhouse scenario rendering the planet completely uninhabitable at over 200 degrees. The uncertainty creates a tension you can feel physically as you scan the data. Which of these worlds is the real Kepler-22b? The answer lies locked in spectroscopic signals too faint for current instruments to detect definitively. The not knowing hangs in the room like an unresolved chord, simultaneously frustrating and tantalizing in its possibilities. Water plays a fundamental role in regulating planetary climates through what scientists call the water cycle feedback. As a planet warms, more water evaporates into its atmosphere. Water vapor is itself a greenhouse gas, potentially creating a positive feedback loop of additional warming. However, increased water vapor also leads to more cloud formation, which can reflect sunlight back to space and cool the planet, a negative feedback mechanism. The balance between these competing feedbacks helps determine whether a planet maintains stable temperatures conducive to life or spirals into climate extremes. On the monitors displaying climate simulations for Kepler-22b, these water feedback processes appear as complex flows and cycles, hypnotic in their constant motion. You find yourself leaning closer to the screens, watching the dance of water between simulated atmosphere and hypothetical oceans, thinking about how similar dynamics shaped Earth's climate history. A planet's position in the habitable zone also affects its atmospheric chemistry in ways critical for potential life. Too close to the star, and photochemical reactions can generate smog-like hydrocarbons that trap heat and trigger a runaway greenhouse effect. Too far, and carbon dioxide can condense out of the atmosphere, reducing the greenhouse warming necessary to maintain liquid water. Kepler-22b's position in its habitable zone suggests it could avoid both these extremes, maintaining a stable atmospheric chemistry over geological timescales. The simulations show chemical reaction networks unfolding in its hypothetical atmosphere, the formation and destruction of molecules visualized as fluctuating concentrations across latitude and altitude. The complexity of these models is staggering, yet they represent simplified approximations of the actual atmospheric chemistry that might exist on this distant world. Another factor influencing habitability is the presence or absence of a large moon. Earth's unusually large moon stabilizes our axial tilt, preventing chaotic variations that would lead to extreme climate swings. Mars, lacking such a stabilizing influence, has experienced dramatic changes in axial tilt over geological time, contributing to its loss of habitability. Does Kepler-22b have a moon? Current instruments cannot detect one, but the question remains relevant for understanding the planet's long-term climate stability. The simulations include scenarios both with and without a large moon, revealing how different the climate history might be under each condition. Without a moon, the models show axial tilt varying chaotically over millions of years, creating periodic ice ages followed by extreme warming events, a challenging environment for complex life to evolve within. The outer edge of the habitable zone presents its own set of considerations. Too far from the star, and a planet might enter a snowball state, where reflective ice covers more of its surface, reflecting away even more sunlight and cooling the planet further. This positive feedback can lock a world in a deep freeze that might be difficult to escape without a major change in conditions, such as increased volcanic outgassing of greenhouse gases. Kepler-22b's position suggests it likely avoids this snowball risk under most atmospheric composition scenarios, another point in favor of its potential habitability. The simulations show how even with lower greenhouse gas concentrations, the planet receives enough stellar energy to maintain liquid water across much of its surface. The balance appears precarious from some perspectives, robust from others, dependent on the specific atmospheric composition and circulation patterns that remain unknown. Cometary impacts represent another environmental factor, influenced by a planet's position relative to its star. Impacts deliver both water and organic compounds to planetary surfaces, potentially seeding the ingredients for life. However, they also cause extinction-level environmental disruptions when large enough. A planet's location in its stellar system affects the frequency and velocity of these impacts. The displays show impact simulations for Kepler-22b based on models of its stellar system architecture. Without knowing whether the system contains asteroid belts or outer gas giants that might shepherd icy bodies inward, the uncertainty in these models remains high. You watch the statistical predictions of impact rates with a mixture of scientific detachment and visceral response, each simulated impact representing both a potential origin for life and a catastrophic reset button for any biology that might have developed. The quality of light reaching a planet's surface influences not just temperature, but biological processes directly. Photosynthesis on Earth evolved to utilize specific wavelengths of sunlight, primarily in the red and blue portions of the visible spectrum. Kepler-22's slightly different spectral output might drive the evolution of photosynthetic organisms using different pigments to capture energy most efficiently from the available light. The displays show predicted photosynthetically active radiation levels at Kepler-22b's surface under various atmospheric scenarios. In some models, the light reaching the surface would support Earth-like photosynthesis with only minor adaptations. In others, more significant evolutionary innovations would be required. You find yourself wondering what alien vegetation might look like, adapted to capture the particular quality of light from a star 620 light-years away. Stellar lifetime provides the ultimate boundary condition for planetary habitability. Stars gradually increase in luminosity as they age, eventually swelling into red giants that engulf their inner planets before collapsing into white dwarfs. This fate awaits both our Sun and Kepler-22, though on different timescales. The evolutionary models for Kepler-22 indicate it will remain in its stable main sequence phase for approximately 10 to 15 billion years total. Given its estimated current age of 5 billion years, this suggests Kepler-22b might remain in the habitable zone for another 5 to 10 billion years, potentially longer than Earth will remain habitable as our own Sun brightens. The thought creates a strange sensation, a mixture of cosmic perspective and personal insignificance. These timescales dwarf not just human lifespans, but the entire history of our species. As you step back from the monitors, taking in the full sweep of data about Kepler-22b's position in its habitable zone, and the complex relationship with its star, a pattern emerges from the individual details. This distant world exists in a state of delicate cosmic fortune, orbiting at just the right distance from a stable, long-lived star of just the right type. Among the thousands of exoplanets discovered, few occupy such a seemingly perfect position. Yet this apparent perfection remains theoretical, dependent on properties we cannot yet measure directly. The true nature of Kepler-22b, whether paradise, purgatory, or something in between, awaits instruments powerful enough to pierce the veil of 620 light-years and reveal its atmospheric composition, surface conditions, and potential for harboring life. What remains undeniable is that Kepler-22b's orbital parameters place it in a category of special interest. planets with the basic prerequisites for habitability. As our ability to characterize exoplanets improves, this world will be among the prime targets for deeper investigation. The air seems to vibrate with anticipation as you consider how future observations might transform our understanding of this distant world, perhaps revealing whether we share our universe with other living beings. The day ends, but the simulations continue running, processing probabilities and projections deep into the night. Tomorrow will bring new data, refined models, and perhaps unexpected insights into the nature of this world orbiting in the perfect zone around its star. But for now, the most important question about Kepler-22b remains unanswered. Could it be a second Earth, or simply another barren world among billions, distinguished only by its tantalizing orbit in the narrow band where life as we know it might possibly exist? The size of a world shapes everything about it, from its ability to retain an atmosphere to the evolutionary pathways of any potential life forms. As you enter the planetary physics laboratory, the first thing you notice is the three-dimensional holographic projection of Kepler-22b floating in the center of the room. The scale indicator shows its diameter approximately 29,000 miles across, or about 2.4 times larger than Earth. The blue-green sphere rotates slowly, its hypothetical continents and oceans shifting in and out of view, an educated guess rendered in light and shadow. This supersized Earth analog immediately creates a visceral reaction. Your mind struggles to comprehend the scale. A world where the horizon would appear more distant, where the curvature of the planet would be less pronounced when viewed from its surface. The projection casts a soft glow across your face as you circle it, trying to internalize what it would mean to stand on a planet of this magnitude. Size alone tells only part of the story. Mass determines gravity, and gravity affects nearly every aspect of planetary science and biology. Without direct measurements, astronomers must estimate Kepler-22b's mass based on its radius and assumptions about its density. The range of possibilities appears on the adjacent screen between 8 and 25 times Earth's mass depending on composition. This uncertainty creates three distinct possibilities for Kepler-22b's fundamental nature. At the lower end of the mass range, it could be a rocky super-Earth with mountains, oceans, and a relatively thin atmosphere. In the middle range, it might be an ocean planet with a solid core surrounded by thousands of miles of water. At the higher end, it could be a mini Neptune with a small rocky core, a deep layer of exotic high-pressure ices, and a thick hydrogen-helium atmosphere. Each scenario creates dramatically different surface gravity. The calculations display on the screen. If Kepler-22b has Earth-like density and 2.4 times Earth's radius, its surface gravity would be approximately 2.4 times stronger than what you feel right now. The implications send a shiver through your muscles. On such a world, your 200-pound weight would translate to 480 pounds. Every movement would require significantly more effort. Simply standing would strain your skeletal structure and cardiovascular system. The physiological effects of such gravity extend far beyond mere discomfort. The laboratory contains a high-gravity simulation chamber where researchers can experience temporarily increased gravitational force. Scientists who have spent time in the chamber report that even brief exposure to twice Earth's gravity causes rapid fatigue, restricted breathing, and difficulty concentrating. Blood pools in the lower extremities, making it harder for the heart to pump it back up to the brain. At 2.4 times Earth gravity, these effects would be even more pronounced. What would this mean for potential life on Kepler-22b? The answer depends partly on the scaling laws of biomechanics. As you watch the simulations of hypothetical Kepler-22b organisms, you notice how they differ from familiar Earth creatures. Their limbs appear thicker, their bodies more compact. In high gravity, the square cube law becomes even more limiting. As an organism grows larger, its weight increases with the cube of its size, while the strength of its supporting structures increases only with the square. This suggests that if complex life exists on Kepler-22b, it would likely be shorter and more robust than comparable Earth species. The tallest trees might reach only half the height of Earth's redwoods. The largest animals would be more squat and powerful. Flying would require stronger muscles and greater wing area, possibly making aerial creatures rarer or more specialized. The slow-motion animations of theoretical Kepler-22b fauna show creatures that seem familiar yet alien, recognizable forms compressed and strengthened to withstand the crushing pull of a super-Earth's gravity. The temperature in the laboratory seems to drop as you contemplate the evolutionary pressures of such a world. The constant struggle against gravity would shape every adaptation, every biological innovation. Circulatory systems would need to generate higher pressures to move blood upward against gravity. Skeletal structures would require greater density and different arrangements to support weight effectively. The entire trajectory of evolution would follow a different path under such conditions. High gravity would affect geological processes as well. Mountain building would work against greater gravitational force, potentially resulting in a flatter world with lower mountain ranges. Volcanic eruptions would need more pressure to overcome the gravitational pull, perhaps leading to fewer but more explosive events when they do occur. Erosion would happen more quickly as water and wind carried greater energy in their constant movement downhill. The scientists working in the lab have created detailed topographical models of potential Kepler-22b landscapes. These appear on a separate display, showing a world where mountains rarely exceed 15,000 feet in height, roughly half the elevation of Mount Everest. River systems cut deeper channels, flowing with greater energy. Impact craters appear shallower and wider than their Earth counterparts, the result of material slumping more readily under increased gravitational pull. Atmospheric effects of high gravity add another layer of complexity. Greater gravitational force compresses the atmosphere, creating higher pressure at the surface. This compression generates more friction as air masses move, potentially resulting in stronger weather systems despite the overall atmospheric density. Wind speeds in storms might reach extraordinary levels, creating selection pressure for streamlined organisms and plants with exceptional anchoring systems. The lab's atmospheric simulation tank demonstrates these principles, with colored gases swirling in accelerated time to show how weather patterns might form and dissipate on a high-gravity world. The movements appear both familiar and strange, recognizable cyclonic patterns that evolve more rapidly and intensely than their Earth counterparts. The colors shift from blue to purple to deep red as pressure zones interact, a visual representation of atmospheric dynamics under alien conditions. Ocean behavior would change dramatically as well. Higher gravity increases the pressure gradient in water, affecting everything from wave formation to current systems. The physical oceanography models show that waves on Kepler-22b's hypothetical oceans would be lower in height, but carry significantly more energy. Tidal forces already influenced by the planet's star would generate different patterns of oceanic circulation. Marine life forms would need to adapt to these high-pressure, high-energy conditions. The impact of size and gravity on a planet's internal structure appears on yet another display. Larger planets generate more internal heat during formation and retain it longer due to their lower surface area to volume ratio. This extended heat retention affects geological activity, potentially keeping Kepler-22b geologically active for billions of years longer than Earth. The cross-sectional diagram shows a molten core surrounded by a convecting mantle, driving plate tectonics that might operate somewhat differently than on our world. This extended geological activity has profound implications for planetary habitability. On Earth, the carbon silicate cycle regulates atmospheric carbon dioxide levels over geological timescales, acting as a thermostat that helps maintain relatively stable climate conditions. A geologically active super-Earth might have a more robust version of this planetary thermostat, potentially providing greater climate stability over multi-billion-year timescales. The sound of the laboratory's geophysical modeling computer rises to a higher pitch as it processes increasingly complex simulations of Kepler-22b's internal dynamics. The heat from the machine fills the room, a tangible reminder of the enormous computational power needed to model these systems and of the immense energies involved in planetary processes. Your shirt clings slightly to your back as you move closer to examine the results appearing on the screen. Planetary magnetic fields represent another characteristic influenced by size and internal structure. Larger, more massive planets with molten cores can generate stronger magnetic fields through the dynamo effect. The simulations suggest that if Kepler-22b has a composition similar to Earth's, its magnetic field could be several times stronger than our own. This enhanced magnetic protection would better shield its atmosphere from stellar wind erosion and cosmic radiation, creating more favorable conditions for surface life. The magnetic field visualization appears as undulating lines of force surrounding the planet model, a protective cocoon extending far into space. The strength of this hypothetical field creates a larger magnetosphere than Earth's, potentially extending protection to any moons that might orbit Kepler-22b. The implications for atmospheric retention and surface radiation levels create another positive factor for potential habitability. Yet size and gravity create significant challenges for any hypothetical technological civilization that might arise on such a world. The rocket equation becomes dramatically more punishing when launching from a higher gravity planet. The screen displays the sobering calculations. Achieving orbit from a planet with 2.4 times Earth's gravity requires approximately 2.4 times the fuel for the same payload. This exponentially increases the difficulty of developing space travel. The implications ripple through imagined technological development paths. A civilization emerging on Kepler-22b might focus more on atmospheric rather than orbital technologies, developing advanced aircraft instead of spacecraft. Space exploration would likely begin much later in their technological evolution, requiring more sophisticated materials and propulsion systems before becoming feasible. The challenges might spur innovation in completely different directions than humanity has pursued. What about human exploration or potential colonization of Kepler-22b? The high-gravity environment would create severe obstacles. Long-term exposure to forces above 1.5 times Earth gravity causes cardiovascular problems, muscle atrophy and bone density abnormalities, even in physically fit individuals. The medical readouts from experimental high-gravity studies scroll across one of the monitors, showing alarming changes in blood pressure, heart function and stress hormone levels after just 72 hours in elevated gravity. Various technological mitigations appear in the engineering schematics on adjacent screens: exoskeletons to support human movement, specialized cardiovascular support systems, and habitats designed to rotate to create lower apparent gravity. Even with these adaptations, long-term human presence on the surface of a high-gravity super-Earth would likely be limited to short rotations, with most habitation occurring in orbital facilities where gravity could be controlled. The prospect of biological adaptation raises even more complex questions. Human embryonic development is calibrated for Earth-specific gravity. The cellular processes of differentiation, the formation of the cardiovascular system, and the development of the musculoskeletal structure all occur under the precise conditions of 1G. Development in significantly higher gravity would likely result in serious abnormalities. This suggests that even if humans could visit Kepler-22b, creating a self-sustaining colony through natural reproduction might prove impossible without genetic engineering or artificial gravity environments. The air in the laboratory feels suddenly heavier as you contemplate these limitations, a psychological reaction to contemplating life under crushing gravity. You shift your weight unconsciously, suddenly aware of how effortlessly you move in Earth's familiar gravitational embrace, a force so constant we rarely consider it until imagining its alteration. If Kepler-22b exists at the higher end of the mass estimate range, it might not be a rocky world at all, but rather a mini Neptune with no solid surface. The simulation shifts to this alternate model, showing a small rocky core surrounded by a vast mantle of exotic high-pressure ices and a thick atmosphere rich in hydrogen and helium. This world would offer no surface for life as we know it to evolve upon, though the boundary between the atmosphere and the high-pressure mantle might harbor exotic biochemistries utterly unlike anything on Earth. The uncertainty about Kepler-22b's fundamental nature, rocky super-Earth, ocean world or gaseous mini-Neptune, represents one of the most significant unknowns in exoplanet science. The laboratory contains physical models of all three possibilities, each occupying its own pedestal. As you move between them, touching the smooth surface of each representation, the difference in their implications becomes tactile. One model feels cool and solid like stone, another smooth and yielding like water, the third almost insubstantial, representing compressed gas. Recent research has identified a potential transition point in planetary size. Worlds larger than approximately 1.5 to 2 Earth radii often appear to have substantial gaseous envelopes rather than being predominantly rocky. At 2.4 Earth radii, Kepler-22b lies very near this transition point, creating genuine ambiguity about its composition. The statistical models on the screen show the probability distribution across different composition types, with no single scenario clearly dominating the others. The determination of Kepler-22b's true nature awaits more powerful observational techniques. Future space telescopes might directly measure its mass through more precise radial velocity observations, revealing its density and thus its likely composition. Transmission spectroscopy during transits could potentially detect the signatures of a substantial atmosphere or indicate a predominantly rocky world. Until then, all three possibilities must be considered equally in scientific analyses. The implications of each scenario for potential life differ dramatically. A rocky super-Earth could host Earth-like biodiversity, although adapted to higher gravity conditions. An ocean world might support marine organisms throughout a global water column thousands of miles deep, with physical conditions varying enormously with depth. A mini-Neptune would likely be inhospitable to life as we understand it, though even this assumption reflects the limitations of our imagination, rather than definitive knowledge about the potential adaptability of life. The challenge of determining Kepler-22b's size with greater precision involves overcoming significant observational limitations. The planet's transit across its star reveals its diameter relative to the star's size, but uncertainties in stellar parameters propagate into uncertainties about planetary size. Recent refinements in stellar modeling have narrowed the error bars somewhat, but a margin of uncertainty remains. This uncertainty exists not just for Kepler-22b, but for virtually all known exoplanets. What appears on paper as a precise value, 2.4 Earth radii, actually represents the central value in a probability distribution. The true radius could be as small as 2.1 or as large as 2.7 Earth radii, with corresponding variations in estimated surface gravity. As the day in the laboratory progresses, researchers adjust parameters in their models, exploring the full range of possibilities within the observational constraints. Each adjustment ripples through the simulations, creating slightly different versions of Kepler-22b. The holographic projection morphs subtly as the radius input changes, growing slightly larger or smaller. The gravitational field strength indicator shifts accordingly, along with all the dependent biological and geological models. This systematic exploration of parameter space represents the heart of exoplanet science, acknowledging uncertainty while rigorously investigating all possibilities consistent with available data. Rather than settling on a single best guess about Kepler-22b's nature, scientists maintain multiple working models ready to discard or refine them as new observations become available. The fundamental question of size and gravity connects to broader issues in planetary system architecture. Super-Earths and mini-Neptunes constitute the most common known exoplanet types in the galaxy, yet our solar system contains none. This absence represents one of the most puzzling features of our planetary system compared to the galactic norm. Understanding worlds like Kepler-22b might provide insight into why our home system developed along a different trajectory. Various formation theories appear on the theoretical model screen, showing how different initial conditions in protoplanetary disks might lead to the formation of super-Earths in some systems but not others. The simulations run forward in accelerated time, showing dust and gas coalescing into planetary bodies of various sizes depending on the starting parameters. In some runs, multiple Earth-sized worlds form, in others super-Earths dominate. The evolutionary history of a super-Earth likely differs significantly from Earth's own development. The greater gravitational well would accumulate and retain volatiles more effectively during formation, potentially resulting in a more substantial primordial atmosphere. This initial condition would set the stage for a different atmospheric evolution over billions of years, possibly creating surface conditions unlike anything in our solar system. As the day winds toward evening, the laboratory lights dim slightly to reduce eye strain during extended model analysis. The blue glow of the holographic projection casts elongated shadows across the room. The central question remains unresolved. What is Kepler-22b really like? Is it a massive rocky world with mountains and oceans under crushing gravity? A water world with no land, where life might have evolved in a global ocean? Or a gas-shrouded mini-Neptune with no solid surface at all? The answer lies encoded in light that left Kepler-22b 620 years ago, currently beyond our technological ability to fully decipher. But each refinement in observational techniques brings us closer to the truth. The air in the laboratory feels charged with the potential of future discoveries as researchers prepare for another day of investigating this distant enigmatic world and the profound implications of its size and gravitational influence. The true nature of a distant world reveals itself most clearly through the whispers of its atmosphere. As you step into the spectroscopy laboratory, the first sensation that strikes you is the distinctive ozone smell from the high-voltage equipment used to generate calibration spectra. Banks of specialized instruments line the walls, each designed to tease apart the faint signatures of molecular absorption imprinted on starlight as it passes through the atmospheres of distant worlds. At the center of the room, a large monitor displays the current best spectral data for Kepler-22b, a series of lines and curves that to the untrained eye might seem like random noise, but to the scientists here represent tantalizing clues about a world 620 light-years away. The challenge of detecting an exoplanet's atmosphere stretches modern technology to its limits. When Kepler-22b transits its star, a tiny fraction of the starlight passes through the planet's atmospheric limb, picking up absorption features from whatever gases are present. These spectral fingerprints arrive at Earth riding on a beam of light already dimmed by the vast distance, contaminated by our own atmosphere, and overwhelmed by the direct glare of Kepler-22 itself. Extracting meaningful information from this whisper-faint signal requires both cutting-edge instrumentation and sophisticated statistical techniques. The spectrographs arrayed around the laboratory represent different approaches to this challenge. Some analyze visible light, others focus on infrared wavelengths. Some use high-resolution gratings to spread light into thousands of precisely measured channels. Others employ lower resolution but higher sensitivity to capture broader features. Each offers a different perspective on the atmospheric puzzle, like distinct senses providing complementary information about the environment. When combined, these various spectroscopic measurements begin to reveal patterns. The monitor transitions to show a composite spectrum, the result of hundreds of hours of observation time on multiple telescopes. Even with this Herculean effort, the signal remains frustratingly indistinct, a series of possible absorption features with wide error bars attached to each. The air in the room feels suddenly tense as you realize how thin the evidence remains, how challenging it is to characterize a world we can never directly see. What molecules might these tentative spectral features represent? The screen shifts to show a comparison between the observed spectrum and models for various potential atmospheric compositions. Molecular oxygen would create a distinctive absorption band at 760 nanometers, but no clear signature appears at this wavelength in the Kepler-22b data. Water vapor should produce characteristic absorption in the near-infrared, around 1.4 and 1.9 micrometers. Here the data shows possible matches, though the statistical significance remains marginal. Perhaps the most intriguing feature appears in the thermal infrared, around 15 micrometers, where carbon dioxide creates a strong absorption band. The data shows a depression in this region that matches the expected pattern, suggesting that Kepler-22b's atmosphere might contain this crucial greenhouse gas. Your pulse quickens at the implication. Carbon dioxide in an atmosphere around a potentially habitable world hints at active geological cycles, perhaps even similar to those that have helped regulate Earth's climate for billions of years. The uncertainty in these detections remains substantial. Each potential identification comes with a confidence level, most hovering around 60 to 70%, suggestive but not definitive. As the scientists process new observations that arrived overnight, you can feel the tension in their movements, the careful attention they pay to calibration procedures. Each tweak to the analysis pipeline might reveal a clearer signature or expose a previously unrecognized systematic error. The atmosphere of a planet tells a story that extends far beyond its current state. It records the history of formation, evolution, and potential biological activity. An atmosphere rich in oxygen and ozone might suggest the presence of photosynthetic life, as these highly reactive gases would quickly disappear without continuous replenishment. Methane alongside oxygen would strengthen the case further, as these gases rapidly react with each other and must be constantly resupplied to coexist. No such clear biosignatures appear in the current Kepler-22b data, but the limitations of current instruments mean this absence of evidence cannot be considered evidence of absence. The detection of oxygen at levels similar to Earth's atmosphere would require sensitivity beyond what today's telescopes can achieve at Kepler-22b's distance. The screen displays sensitivity thresholds as horizontal lines across the spectrum, showing which gases remain below the detection limits. The room contains physical models of different potential atmospheric compositions for Kepler-22b, each sealed inside a transparent cylinder. One contains a mixture similar to Earth's nitrogen-oxygen atmosphere. Another a denser envelope rich in carbon dioxide like Venus. A third a hydrogen-helium-dominated composition more akin to Neptune. As you move between these displays, reading the composition details on each label, you're struck by how dramatically different a world would be under each scenario. Atmospheric pressure fundamentally shapes surface conditions. On Earth, standard pressure at sea level allows water to exist simultaneously as solid, liquid, and gas within the habitable temperature range. On Venus, the crushing atmospheric pressure of 92 times Earth's keeps the surface hot enough to melt lead. If Kepler-22b has retained a substantial primordial envelope of hydrogen and helium, its surface pressure could be hundreds of times greater than Earth's, creating exotic states of matter and precluding life as we understand it. The atmospheric circulation models on another screen show how different compositions would create different weather patterns. In an Earth-like atmosphere, the rotation of the planet would break circulation into latitude-dependent cells and bands. A thicker atmosphere would show less differentiation and more heat transport from the day side to the night side. The simulations run in accelerated time, showing how storm systems might form and dissipate, how heat would flow from equator to poles. Your skin prickles slightly as the air conditioning cycles on, coinciding with a shift in the simulation to show polar vortices forming in a hypothetical winter hemisphere of Kepler-22b. The timing creates a momentary sensory link between your physical environment and the distant world under study, a reminder that atmospheric dynamics follow the same physical laws whether on Earth or 620 light-years away. One key atmospheric component that remains particularly difficult to detect is nitrogen. Despite comprising 78% of Earth's atmosphere, nitrogen produces few distinctive spectral features. Its presence must often be inferred indirectly, through pressure broadening effects on other molecular lines. Yet nitrogen plays a crucial role in habitability, acting as a pressure-increasing buffer gas that helps maintain liquid water under the right temperature conditions. The screen transitions to show the modeled effect of different nitrogen abundances on Kepler-22b's climate. With little or no nitrogen, the greenhouse effect from water vapor and carbon dioxide must do most of the work to maintain habitable temperatures, potentially creating an unstable climate susceptible to either runaway freezing or runaway heating. With abundant nitrogen, the climate gains stability and robustness against perturbations. Atmospheric chemistry extends beyond the simple presence or absence of key molecules. Complex chemical networks operate in any planetary atmosphere, driven by energy inputs from the parent star, cosmic rays, lightning, and potentially biology. These networks can produce unexpected compounds and create disequilibrium states that might be detectable through careful spectroscopic analysis. The chemistry modeling station in the corner of the lab runs continuous simulations of reactions occurring in different atmospheric compositions under Kepler-22b's proposed conditions. The display shows molecules being created and destroyed, reaction pathways branching and converging. In some scenarios, complex organic haze forms in the upper atmosphere, potentially shielding the surface from harmful radiation, but also reducing the detectability of compounds lower in the atmosphere. High-energy ultraviolet radiation from Kepler-22 would drive photochemical reactions in the upper atmosphere, breaking apart stable molecules and allowing their components to recombine in new forms. This photochemistry creates stratospheric ozone on Earth, protective shield against biologically damaging ultraviolet light. The simulations suggest that if Kepler-22b has an oxygen-rich atmosphere, it would likely develop a similar ozone layer, potentially enabling surface life to evolve without excessive radiation damage. The laboratory maintains a series of environmental chambers where researchers can physically simulate atmospheric conditions on other worlds. Through the viewing window of one such chamber, you observe a reddish haze forming under ultraviolet lamps, similar to the organic smog produced in experiments simulating Titan's atmosphere. Another chamber contains a mixture approximating a carbon dioxide water vapor atmosphere under high pressure, with condensation forming on its cooled surfaces. These physical simulations complement the computer models, allowing researchers to observe chemical phenomena that might be overlooked in purely theoretical approaches. The combination of observation, physical experimentation, and computational modeling represents the best strategy for understanding a world too distant to study directly. Your nose detects a faint, unfamiliar chemical odor leaking from one of the sealed chambers, a tangible reminder that alien atmospheres would contain compounds your senses have never evolved to process. One critical question about Kepler-22b's atmosphere relates to its vertical structure. Temperature typically decreases with altitude in the lowest atmospheric layer, the troposphere, then increases in the stratosphere due to absorption of ultraviolet radiation. This thermal inversion creates a stable boundary that influences weather, climate, and the distribution of chemical compounds. The atmospheric structure models show different possibilities for Kepler-22b, varying based on atmospheric composition and the spectrum of its star. A world with substantial methane might develop a stratosphere even warmer than Earth's, as methane absorbs solar radiation effectively at specific wavelengths. The display shows temperature profiles as colored vertical lines, each representing a different atmospheric composition scenario. The diversity of possibilities underscores how much remains unknown about this distant world. If Kepler-22b possesses a substantial atmosphere, Its color when viewed directly would result from complex scattering and absorption processes. The wavelength-dependent scattering of sunlight gives Earth its blue appearance from space. A different atmospheric composition would create different visual effects. The visualization screen shows artistic renderings of how Kepler-22b might appear under various atmospheric assumptions: blue like Earth with a nitrogen-oxygen atmosphere, reddish-orange with a hydrocarbon haze, whitish with extensive cloud cover, or various other possibilities. These visual representations, while scientifically informed, remind you how little we truly know about this world's appearance. No telescope can directly image Kepler-22b's disk. It appears only as an indirect shadow crossing its star. Its colors, its cloud patterns, the quality of light filtering through its atmosphere to reach its surface, all remain in the realm of educated speculation, constrained by physics but not yet confirmed by observation. The presence and composition of clouds significantly impacts both climate and our ability to detect atmospheric components. Water clouds on Earth reflect sunlight, cooling the planet while obscuring the lower atmosphere from external observation. Different cloud-forming compounds would create different effects. Ammonia clouds, water ice clouds, carbon dioxide ice clouds, or even exotic metallic vapor clouds could all potentially exist depending on atmospheric composition and temperature structure. The cloud formation models on one of the laboratory's specialized workstations show how different atmospheric compositions would condense at different altitudes. Some scenarios result in multiple distinct cloud layers, others in permanent global cloud cover, still others in relatively clear skies with only scattered cloud formation. Each scenario affects the planet's albedo, the fraction of incoming starlight reflected back to space, consequently altering surface temperature and potential habitability. Your eyes are drawn to a particularly striking simulation showing towering storm clouds forming along the terminator, the boundary between day and night sides of the planet. In this model, intense heating on the day side drives moisture into the upper atmosphere, where it circulates to the cooler night side and precipitates in spectacular storm systems. The visualization shows lightning illuminating these clouds from within, a reminder that atmospheric dynamics create environments of awesome power regardless of the specific molecular composition. The laboratory contains a specialized chamber for the study of cloud microphysics, the formation, growth, and dissipation of cloud particles under various conditions. Through its viewport, you observe tiny droplets nucleating and growing within a carefully controlled environment designed to mimic potential conditions in Kepler-22b's atmosphere. The process appears both familiar and alien, following the same physical principles that create clouds on Earth but operating under different temperature, pressure, and compositional constraints. Atmospheric stability represents another critical factor for habitability. Some atmospheric compositions remain stable over billions of years, while others evolve rapidly due to escape to space, chemical reactions, or geological interactions. The screen transitions to show the modeled long-term evolution of different potential atmospheres for Kepler-22b, running forward over simulated billions of years. In some scenarios, the atmosphere remains relatively constant, maintained by a balance of sources and sinks similar to Earth's long-term stability. In others, the atmosphere undergoes dramatic transitions, hydrocarbon hazes forming and then dissipating, water slowly photodissociating and allowing hydrogen to escape to space, carbon dioxide being sequestered into carbonates or building up to Venus-like levels. The timescales of these processes range from thousands to billions of years, each representing a different potential history and future for this distant world. The evolutionary pathways depend strongly on factors we cannot yet measure directly. The presence or absence of an internal magnetic field would affect atmospheric retention over time. Geological activity would influence gas exchange between the interior and the surface. The spectral energy distribution of Kepler-22 during its younger, more active phase would have subjected the primordial atmosphere to different radiation conditions than it experiences today. As the models run, showing atmospheric evolution over simulated eons, you're struck by the temporal scale being contemplated. The atmosphere of Kepler-22b that we observe today via its spectral signatures left that distant world 620 years ago. It represents a single snapshot in a planetary evolution spanning billions of years. The moment we're observing is simultaneously ancient from a human perspective and essentially current from a geological one. The impact of life on atmospheric composition cannot be overlooked. On Earth, the oxygen-rich atmosphere results directly from biological activity. Before photosynthetic organisms evolved and spread across our planet, Earth's atmosphere contained little free oxygen. The Great Oxygenation Event approximately 2.4 billion years ago represents one of the most significant atmospheric transitions in our planet's history, driven entirely by biological processes. If life exists or existed on Kepler-22b, it might similarly transform its atmosphere into a state of chemical disequilibrium detectable across interstellar distances. The Biogeochemical Modeling Station simulates how different forms of life might alter atmospheric chemistry over time. Some scenarios show oxygen building up as on Earth, others explore alternative metabolisms that might produce different atmospheric biosignatures, such as complex organics, ammonia, or other compounds. These biosignature models proceed cautiously, aware of the potential for false positives. Abiotic processes can sometimes mimic the chemical signs of life. Photochemical reactions in the upper atmosphere can produce organic compounds. Outgassing from a geologically active interior can release reduced gases that might otherwise suggest biological activity. The distinction between biosignatures and their abiotic mimics represents one of the most challenging aspects of remote atmospheric characterization. The laboratory maintains physical models of different types of organisms that might exist in various atmospheric compositions. These range from familiar forms similar to Earth bacteria to more speculative designs adapted to exotic chemistry. As you examine these models, you're reminded that the definition of habitable depends entirely on what type of life we're considering. What would be toxic to Earth life might be perfectly suitable for organisms evolved under different conditions. This concept of atmospheric habitability versus biological adaptability creates a matrix of possibilities displayed on the central screen. A traditional habitable zone considers only Earth-like life in Earth-like atmospheres. A more expansive view considers how different atmospheric compositions might support different chemical foundations for life. The matrix shows dozens of combinations, from the familiar oxygen-nitrogen atmosphere supporting water-based biochemistry to exotic possibilities like hydrocarbon atmospheres supporting silicon-based life forms. Whether any of these theoretical possibilities actually exist on Kepler-22b remains unknown. The current spectroscopic data provides only the broadest constraints on atmospheric composition, with wide error bars and multiple interpretations possible. The scientists in the laboratory maintain a careful balance between imagination and empirical restraint, exploring possibilities while acknowledging the limitations of current knowledge. The next generation of telescopes promises to dramatically improve our understanding of exoplanet atmospheres. The specialized instruments being developed will provide higher spectral resolution, better signal-to-noise ratios, and the ability to observe at wavelengths currently inaccessible. Designs and prototypes for these future observational capabilities occupy one section of the laboratory, representing the bridge between today's tentative detections and tomorrow's more definitive characterizations. As the day in the spectroscopy laboratory draws to a close, the monitors continue displaying the latest analyses of Kepler-22b's possible atmospheric composition. The evidence remains tantalizingly incomplete. Hints of water vapor and carbon dioxide, ambiguous signatures that could represent methane or other organic compounds, absence of clear oxygen features that might result from either lack of oxygen or simply insufficient detection sensitivity. What emerges most clearly is not a specific atmospheric composition, but rather the range of possibilities consistent with current observations. Kepler-22b might possess an atmosphere remarkably similar to Earth's, rich in nitrogen and oxygen, with water vapor and trace gases. It might have a denser envelope dominated by carbon dioxide, creating a greenhouse effect stronger than Earth's but potentially still compatible with liquid water. It might retain a substantial primordial atmosphere of hydrogen and helium, making its surface conditions utterly unlike anything in our solar system. The distinction between these possibilities carries profound implications for the potential habitability of this distant world. As you exit the laboratory, the atmospheric data continues streaming in from telescopes around the world and in space, each new observation narrowing the range of possibilities slightly, bringing us incrementally closer to understanding the true nature of Kepler-22b's gaseous envelope, and the environment it creates on the surface of this enigmatic super-Earth. Water transforms worlds. It shapes geology, enables complex chemistry, and on at least one planet in the universe, serves as the foundation for all known life. As you enter the astrobiological hydrology laboratory, The central display shows a false color image of Kepler-22b, with hypothetical ocean coverage patterns rendered in shimmering blue against the muted browns and greens of theoretical landmasses. The visualization rotates slowly, offering different angles on a world that could be anywhere from bone-dry to completely submerged beneath global oceans hundreds or even thousands of miles deep. The humidity in this section of the research facility runs higher than elsewhere, maintained at 55% to support the various water-based experiments in progress. The air feels slightly heavier in your lungs, a constant reminder of water's universal presence on Earth and its potential significance on distant Kepler-22b. Condensation occasionally forms on the cooler surfaces of equipment, mimicking on a micro scale the hydrological cycles being modeled in the simulations. The fundamental question that drives research in this laboratory sounds deceptively simple. Does liquid water exist on Kepler-22b? The answer remains frustratingly elusive. Current observations cannot directly detect surface water at a distance of 620 light-years. Instead, scientists must rely on indirect evidence, theoretical models and probability assessments based on the planet's known characteristics and our understanding of planetary formation and evolution. The case for water begins with Kepler-22b's position in the habitable zone, at a distance of 0.85 astronomical units from its star, receiving approximately 87% of the stellar energy that Earth receives from the Sun. Kepler-22b orbits in the region where temperatures could allow liquid water to exist on a planetary surface. This orbital sweet spot represents the first piece of circumstantial evidence, suggesting Kepler-22b might be a world where oceans could exist. Temperature alone, however, provides insufficient information. The presence of liquid water depends on both temperature and pressure, which in turn depends on atmospheric composition and density. The phase diagram of water displayed on one of the laboratory screens shows the temperature-pressure combinations where water exists as solid ice, liquid or vapor. An adjacent display shows the same information for exotic water states like supercritical fluids, where the distinction between liquid and gas disappears under extreme pressure and temperature. Models of Kepler-22b's potential surface conditions show several possibilities spanning this phase diagram. If the planet has an Earth-like atmosphere, surface temperatures likely range from approximately 40 to 75 degrees Fahrenheit, comfortably within the liquid water regime. A thicker atmosphere with stronger greenhouse effects could push temperatures higher, potentially creating conditions where open water would readily evaporate. A thinner atmosphere might allow water to exist only in sheltered locations or at specific latitudes. The water content of Kepler-22b likely traces back to its formation history. The current theories of planetary formation displayed on the screen suggest that super-Earths like Kepler-22b often form beyond the snow line, the distance from a star where water freezes into solid ice in the protoplanetary disk. These worlds accumulate substantial quantities of water ice during formation, which later melts as the planets migrate inward to orbits closer to their stars. This formation pathway could make Kepler-22b dramatically more water-rich than Earth. Our planet contains approximately 0.02% water by mass, mostly confined to a thin surface layer. Super-Earths that formed beyond the snow line might contain 10, 20 or even 50% water by mass, enough to create global oceans hundreds or thousands of miles deep with no land breaking the surface anywhere. The laboratory maintains physical models of different possible water distributions on Kepler-22b. One shows a world similar to Earth, with continents and oceans covering roughly similar proportions of the surface. Another displays a planet with scattered island chains rising from a world-spanning ocean. A third depicts a true water world, completely covered by a global ocean with no land visible anywhere. As you move between these models, the implications of each scenario for potential habitability become increasingly apparent. Water affects everything from climate stability to geological cycles to the possibility of complex life. Earth's relatively balanced land-ocean ratio creates climate-stabilizing feedbacks through processes like silicate weathering, where rainfall interacts with exposed rock to sequester atmospheric carbon dioxide. A world covered entirely by oceans would lack this crucial feedback mechanism, potentially leading to less stable long-term climate conditions. The screen transitions to show ocean circulation models for different potential Kepler-22b scenarios. If the planet rotates at a rate similar to Earth, its oceans would develop complex current systems driven by the Coriolis effect, with heat transported from equator to poles through massive oceanic conveyor belts. These currents would play a crucial role in determining the planetary temperature distribution and local environmental conditions. In a deep ocean scenario, pressure increases with depth at a rate of approximately 0.44 pounds per square inch for every foot of depth. The pressure at the bottom of Earth's Mariana Trench, approximately 36,000 feet deep, reaches 16,000 pounds per square inch. Now imagine an ocean not 7 miles deep, but 70 or 700 miles deep. The pressure at these depths would create exotic water phases unlike anything found naturally on Earth. The simulations show how water behaves under such extreme conditions. Beyond a certain depth in these hypothetical Kepler-22b oceans, water would transition to exotic high-pressure forms, ice fells, and supercritical fluids where the distinction between liquid and gas disappears. These phases have dramatically different properties from the familiar water we experience daily, different density, viscosity, solubility, and chemical behavior. The laboratory contains specialized high-pressure chambers designed to study these exotic water phases under controlled conditions. Through the small diamond viewing ports, you observe water compressed to densities nearly twice that of normal liquid water, behaving with significantly different physical and chemical properties. The sight creates a visceral connection to the potential reality of deep ocean worlds where most of the water exists in these strange, unfamiliar states. What would the transition zones between these different water phases look like in a super-Earth ocean? The models suggest distinct boundary layers where density changes significantly over relatively short vertical distances. These boundaries would affect ocean circulation, heat transport, and the movement of dissolved minerals. In the most extreme cases, the differences between water layers might be as dramatic as the difference between Earth's oceans and atmosphere. The implications for potential life in such environments capture your attention on another screen. Earth's deep ocean trenches host extremophile organisms adapted to crushing pressures, but nothing on our planet experiences the conditions that would exist in the depths of a water world super-Earth. Could life evolve and thrive in supercritical water environments? Could organisms develop biological mechanisms to move between different water phases, adapting to the dramatically different conditions at various ocean depths? The astrobiological simulations explore these possibilities, modeling theoretical metabolic pathways that might function under high-pressure conditions. Some propose organisms using the chemical potential energy available at the boundaries between different water phases. Others suggest life forms that float at specific depths where pressure and temperature combine to create environments suitable for complex chemistry. The theoretical diversity shown in these models reminds you how narrowly confined Earth life is to a tiny slice of the possible parameter space for water-based biology. How might we detect the presence of oceans on Kepler-22b from Earth? The spectroscopic evidence shown on another display reveals potential water vapor signatures in the planet's atmosphere, not conclusive proof of surface oceans, but certainly consistent with their existence. Water vapor in an exoplanet's atmosphere suggests a reservoir of the liquid form, though this relationship becomes complicated in scenarios with unusual atmospheric compositions or temperature structures. More compelling evidence might come from observations of the planet's reflectivity as it orbits its star. Liquid water surfaces have distinct reflective properties that vary with wavelength and viewing angle. The spectrographic analysis station displays models of how Kepler-22b's brightness might change during its orbit if significant portions of its surface were covered by oceans. Current observational technology cannot detect these subtle variations at Kepler-22b's distance, but next-generation space telescopes might achieve the necessary precision. The potential for global oceans raises questions about the mineral content of Kepler-22b's waters. On Earth, the oceans contain dissolved salts at an average concentration of approximately 3.5%. These salts affect water's freezing point, density structure, and chemical behavior. The laboratory maintains tanks simulating different possible compositions for Kepler-22b's oceans, some with Earth-like salinity, others with dramatically different mineral content based on different assumptions about the planet's bulk composition and evolution. In the experimental area containing these simulation tanks, you notice how differently light behaves in waters of varying composition. Some appear clearer than Earth's oceans, others more opaque. The colors range from familiar blue to greenish, yellowish, or even reddish hues depending on dissolved components and suspended particulates. These visual differences serve as a reminder that ocean as a concept encompasses a vast range of possible chemical environments, not just the specific sodium chloride-dominated composition we know on Earth. If Kepler-22b formed as a water-rich world, its internal structure would differ significantly from Earth's. Rather than a relatively thin water layer over a predominantly silicate mantle, it might have a thick shell of high-pressure ice forms surrounding its rocky core. The geophysical models displayed on another screen show how these ice layers would affect heat transfer from the interior, potentially limiting geological activity at the seafloor and changing the planet's overall thermal evolution. These structural differences would have profound implications for the geochemical cycles that help regulate Earth's climate over geological timescales. On our planet, the interaction between water and exposed silicate rocks plays a crucial role in the carbon cycle that helps maintain relatively stable temperatures. A water world with no exposed land and a high-pressure ice barrier between ocean and rocky interior might lack these stabilizing feedbacks, potentially experiencing more extreme climate variations over time. The laboratory's dynamic models explore how such a world might evolve over billions of years. In some scenarios, initial conditions lead to relatively stable states where feedback mechanisms maintain habitable conditions. In others, the absence of crucial geochemical cycles leads to runaway processes, atmospheres stripped away, oceans frozen solid, or greenhouse effects spiraling upward to Venus-like conditions. The stark differences between these potential evolutionary pathways highlights how tightly constrained habitable conditions might be for certain types of water worlds. What about the distribution of water across Kepler-22b's surface? Without direct imaging, scientists must rely on models informed by our understanding of planetary dynamics. If the planet has a similar axial tilt to Earth, it would experience seasonal variations that affect the distribution of surface water. The climate simulations show how potential landmasses might experience wet and dry seasons, how ice caps might expand and contract at the poles, how ocean currents might shift with seasonal changes. The temporal behavior of water takes center stage in another section of the laboratory, where researchers study the potential for weather and climate cycles on Kepler-22b. The holographic display shows cloud formation and precipitation patterns for different potential atmospheric compositions and surface water distributions. Some scenarios depict storm systems larger and more intense than anything on Earth, driven by the increased energy of a larger planet with potentially greater temperature differentials. You watch mesmerized as a simulation shows rainfall on a hypothetical Kepler-22b landscape, water droplets forming in the atmosphere, falling through an alien sky, collecting in streams and rivers that carve the terrain before eventually returning to simulated oceans. The hydrological cycle, that familiar pattern from Earth, playing out with different parameters on a world we've never seen directly. The sight evokes a strange sense of connection, a recognition that the same physical laws that shape our home planet would operate similarly, though not identically, on this distant super-Earth. If Kepler-22b does possess substantial surface water, the implications for potential life become significantly more favorable. All known life requires liquid water as a solvent, though the exact conditions, temperature, pressure, salinity, pH can vary widely across different extremophile organisms. The presence of large-scale liquid water reservoirs would provide environments where prebiotic chemistry might develop into full biological systems, given sufficient time and energy sources. The astrobiological research section of the laboratory explores the various ways that life might utilize water environments on Kepler-22. The models consider not just Earth analogues, photosynthetic organisms using sunlight energy, heterotrophs consuming organic materials, chemotrophs deriving energy from inorganic chemical reactions, but also more exotic possibilities, tailored to the specific conditions that might exist on this super-Earth. What if Kepler-22b's oceans extend for hundreds of miles in depth, transitioning through different water phases? The simulations suggest the possibility of stratified biospheres, distinct ecological zones at different depths, each adapted to the specific pressure, temperature, and chemical conditions of its environment. Life at the surface might resemble Earth's marine ecosystems in broad strokes, while organisms in the high-pressure depths could employ fundamentally different biochemical mechanisms. The extreme depths of potential water-world oceans create environments without direct analogues on Earth. The laboratory maintains specialized chambers simulating these conditions, where researchers test the stability of various organic compounds and the feasibility of different metabolic pathways under high pressures. Through the viewing ports, you observe chemical reactions proceeding differently than they would under Earth normal conditions, some inhibited by pressure effects, others actually enhanced. These experimental results feed into the broader question of habitability. If Kepler-22b is a true water world, with oceans extending hundreds of miles deep, would the high-pressure regions remain habitable by any definition we would recognize? Or would only the surface layers where conditions more closely resemble Earth's oceans provide viable environments for recognizable life forms? The potential for liquid water extends beyond standing oceans to include atmospheric water, ice caps, and subsurface reservoirs. The climate models consider all these possibilities, exploring scenarios where water might exist primarily as ice, with only seasonal melting in warmer regions, or as vapor in a steam atmosphere, condensing only under specific conditions. The distribution between these different phases would depend on the planet's average temperature, atmospheric pressure, and orbital characteristics. One particularly intriguing scenario explored in the laboratory involves a super-Earth with global oceans but active geological processes that create chains of volcanic islands. These islands would provide crucial land-ocean interfaces where more complex biochemical cycles might develop. The models show how such a partial water world might actually prove more conducive to the evolution of complex life than either a predominantly terrestrial planet or a complete water world. The question of ocean depth becomes particularly significant when considering the planet's size and gravity. On a super-Earth with higher gravity, the pressure increase with depth would be more rapid than on Earth. The transition to exotic ice phases would occur at shallower depths, potentially limiting the extent of conventional liquid water environments more severely than on a smaller world. The pressure profiles displayed on the screen show how rapidly conditions would change with depth in Kepler-22b's potential oceans. The evidence for water on Kepler-22b ultimately remains circumstantial. The planet's position in the habitable zone, its size consistent with water-rich super-Earths, and possible atmospheric water vapor signatures all suggest liquid water could exist there. But definitive proof awaits more powerful observational capabilities, space telescopes that can directly analyze the spectral signatures of surface materials or detect the unique light polarization effects of large bodies of liquid water. As day transitions to evening in the laboratory, the simulations continue running, exploring countless permutations of Kepler-22b's potential hydrological systems. The air remains humid, water vapor suspended invisibly all around you, a constant reminder of this molecule's unique properties and its central importance to the question of habitability, not just for Earth but for distant worlds like Kepler-22b that might someday prove to be oases of liquid water in the cosmic desert. The audacious concept of terraforming, actively transforming a planet to make it more Earth-like, represents the convergence of our most advanced science and our most ambitious dreams. As you enter the planetary engineering laboratory, the first thing that strikes you is the scale model of Kepler-22b dominating the center of the room. This three-dimensional representation stands 12 feet in diameter, with removable sections revealing different potential internal structures. Around its equator runs a band of small mechanical manipulators, symbolic representations of the tools humanity might someday deploy to reshape an alien world. The air in this section of the research complex carries the metallic tang of electronics and the subtle scent of the specialized polymers used in architectural models. The temperature feels slightly warmer than in other laboratories, maintained at precisely 75 degrees Fahrenheit, to optimize the performance of the complex simulation systems. Despite the technical environment, there's something almost spiritual about this space, a temple to the breathtaking audacity of believing we might someday redesign worlds circling other stars. Terraforming Kepler-22b would represent a project of unprecedented scope, dwarfing any engineering endeavor in human history. The basic parameters appear on the main display: a super-Earth with approximately 2.4 times Earth's radius and anywhere from 10 to 25 times its mass, orbiting a sun-like star at a distance, allowing for potentially habitable surface temperatures. The known facts end there. Everything else, atmosphere, surface conditions, chemical composition, remains in the realm of reasoned speculation. This fundamental uncertainty creates the first major challenge for any theoretical terraforming project. How can you transform a world whose baseline conditions remain largely unknown? The scientists working in this laboratory approach the problem through scenario analysis, developing distinct terraforming strategies for different possible starting conditions. Their methodical approach breaks down into three primary scenarios: modifying a rocky super-Earth with inadequate atmosphere, taming a runaway greenhouse world similar to Venus, or creating habitable regions on a water world covered by global oceans. The rocky world scenario appears first on the main simulation screen. If Kepler-22b has a solid surface with insufficient atmosphere to maintain Earth-like temperatures and pressures, terraforming would focus on atmospheric enhancement. The traditional approach developed for Mars, releasing carbon dioxide locked in soil and minerals, would likely prove insufficient for a super-Earth with much greater surface area and gravity. More potent greenhouse gases would be required, manufactured and released strategically to trap stellar heat. The simulation shows robotic factories processing regolith, extraction facilities mining the planetary interior, and orbital mirrors focusing additional starlight onto targeted regions. The timeline at the bottom of the display shows centuries passing as the atmospheric pressure gradually increases. You can almost feel the bitter cold of the hypothetical barren landscape slowly warming as manufactured gases trap more of Kepler-22b's stellar energy. Introducing water presents another challenge in this scenario. If Kepler-22b lacks significant surface water, terraformers might redirect small ice-rich asteroids or comets from the outer reaches of the system to impact carefully selected regions. The simulation demonstrates this process, showing trajectory calculations and impact sites selected to distribute water resources optimally across the planet's surface. The violence of these controlled impacts creates a visceral response. You can almost feel the ground shake as billions of tons of ice vaporize on impact, eventually condensing as rainfall to fill newly formed seas. The timeline for this most basic terraforming scenario stretches across nearly 1,000 years. The resource requirements displayed in the sidebar are staggering. Energy consumption measured in zettajoules, material processing on a planetary scale, robotic workforces numbering in the billions. The cost calculation simply shows beyond conventional economic measurement. The second scenario depicts Kepler-22b as a runaway greenhouse world, a super Venus with a dense hot atmosphere, composed primarily of carbon dioxide. Terraforming such a planet would require the opposite approach, removing greenhouse gases to reduce surface temperatures and pressures. The simulation shows massive atmospheric processing stations extracting carbon dioxide and sequestering it in stable mineral forms or launching it into space. This scenario presents even greater challenges than the first. The energy requirements for removing and processing a Venus-like atmosphere scale with the planet's size and gravity. For a super-Earth, the numbers become almost incomprehensible. The timeline extends further 1,500 to 2,000 years of continuous operation. The technical obstacles multiply: materials that can withstand corrosive atmospheric chemistry, energy systems that can function in extreme heat, and autonomous technologies that can operate for centuries with minimal human intervention. As the simulation runs, you notice how the virtual atmospheric pressure gradually decreases, the surface temperature slowly dropping from uninhabitable levels. The visualization shows the planet's appearance changing as the thick cloud layers thin, eventually revealing glimpses of the surface below. There's something profoundly moving about watching a world transform from hell to potential paradise, even in simulation, a testament to the power of the technological sublime. The third scenario presents Kepler-22b as a water world, a planet where global oceans hundreds or thousands of miles deep cover the entire surface. Terraforming such a world wouldn't focus on atmospheric composition, but rather on creating land where none exists. The simulation shows massive platforms being constructed from materials mined from the seabed or asteroids, artificial continents built from the ocean floor up. This approach represents perhaps the most radical departure from traditional terraforming concepts. Rather than modifying existing geography, it would involve creating new landscapes from scratch. The simulation shows how these artificial landmasses would be designed with careful attention to hydrological cycles, with engineered mountain ranges to capture rainfall, river systems to distribute fresh water, and agricultural zones placed in optimal climate regions. The room contains physical models of these hypothetical engineered continents, intricate architectural representations showing transportation networks, agricultural zones, and human habitation areas. Running your fingers over one of these models, you feel the topographical features, mountain ranges, river valleys, coastal plains, all designed rather than formed by natural geological processes. The concept blurs the line between terraforming and world-building in the most literal sense. All three scenarios share common technical challenges that scale directly with Kepler-22b's size. The planet's higher gravity would require more energy for any process involving vertical movement, from atmospheric convection to the water cycle to the growth of terrestrial plants. Materials would need to withstand greater structural stresses. Biological organisms transplanted from Earth would need to adapt to the increased gravitational load on their tissues and circulatory systems. The gravitational simulation chamber in the corner of the laboratory allows researchers to experience approximately 1.5 times Earth's gravity, the highest level safely achievable with current technology, and still well below what would be experienced on Kepler-22b's surface. Spending just 15 minutes in this environment leaves muscles aching and movements labored. The experience drives home the physiological challenges humans would face on a super-Earth, even after successful terraforming. Beyond the physical parameters, the timescales involved in planetary engineering create unique challenges. Any terraforming project would span multiple human generations, requiring social and political structures capable of maintaining consistent effort toward extremely long-term goals. The sociological models running on a separate system explore various governance approaches that might support multi-century engineering projects, from AI-managed systems to specially designed institutional frameworks with embedded intergenerational commitment mechanisms. The display transitions to a section addressing the ethical dimensions of terraforming. The first consideration, whether the planet already hosts indigenous life, remains paramount. Current observational technology cannot definitively determine if microbial or even complex life exists on Kepler-22b. The ethical frameworks developed for terraforming emphasize the primacy of protecting any existing biosphere, no matter how simple, over human modification. This ethical constraint creates a technical requirement for thorough biological survey before any terraforming could begin. The robotic probe designs displayed on a side screen show sophisticated life detection capabilities from atmospheric biosignature analysis to surface sample collection and processing. Any detection of indigenous life would immediately shift the mission from terraforming to xenobiological study, with preservation as the primary objective. If Kepler-22b proves lifeless, terraforming raises different ethical questions about humanity's right to reshape worlds to suit our needs. The philosophical position statements from various research groups show a spectrum of perspectives, from viewing uninhabited planets as blank canvases for human creativity, to considering all natural planetary states as inherently valuable and worthy of preservation. These philosophical differences would shape any actual terraforming attempt as much as the technical challenges. The timeline display shows how our understanding of Kepler-22b will likely evolve long before any terraforming becomes technically feasible. The next 50 years will bring increasingly detailed remote observations, resolving questions about atmospheric composition and surface conditions. The following century might see the first robotic probes dispatched to the Kepler-22 system, an enormous technical challenge given the 620 light-year distance, but likely achievable before any actual terraforming technology. This progressive improvement in our understanding of Kepler-22b would refine terraforming approaches over time. The simulation shows how initial concepts based on limited data would evolve as more detailed information becomes available. What begins as broad scenario planning would gradually converge on specific engineering approaches tailored to the planet's actual conditions. Energy represents perhaps the most fundamental requirement for any terraforming effort. The calculations displayed on one screen show the staggering power needs continuous energy application measured in petawatts, sustained over centuries. Solar collection systems spanning thousands of square miles, fusion reactors operating continuously for decades, power transmission networks covering an entire planet. The infrastructure requirements alone would dwarf anything constructed in human history. The materials science section explores substances that could withstand the conditions on Kepler-22b during different phases of terraforming. Advanced ceramics that remain stable under extreme temperatures, self-healing polymers that can endure centuries of ultraviolet radiation, programmable matter that can reconfigure to adapt to changing conditions. These technologies exist only in preliminary form today, but would be essential for operations on a distant super-Earth. Biological engineering plays a crucial role in all terraforming scenarios. The genetic design stations show organisms modified to serve specific functions in planetary transformation, extremophile bacteria engineered to gradually alter soil chemistry, photosynthetic organisms adapted to different light spectra and atmospheric compositions, pioneer plants with enhanced carbon sequestration capabilities. These modified life forms would serve as living technologies, self-replicating systems performing specific chemical transformations on a planetary scale. The ethical questions surrounding such extensive genetic engineering appear on adjacent displays. Creating organisms specifically designed to transform planetary environments raises profound questions about biological responsibility and ecological risk management. The containment protocols and genetic safeguards under development reflect these concerns, attempting to balance transformation potential against the risk of uncontrolled biological processes. Atmospheric engineering presents particularly complex challenges for a super-Earth like Kepler-22b. The higher gravity means greater mass of gas must be processed to achieve atmospheric modification, while the escape velocity makes it more difficult to remove unwanted atmospheric components by simply allowing them to bleed into space. The engineering designs show massive processing facilities that would capture, separate, and transform atmospheric gases on an industrial scale unprecedented in human history. Water management would present its own specialized challenges. If Kepler-22b air has too little water, importing it would require redirecting and capturing cometary bodies or ice-rich asteroids, a process requiring extraordinary precision in celestial mechanics. If the planet has too much water, creating landmasses would involve either physical barriers against global oceans or actually removing water from the planet, technically possible, but requiring energy expenditures that strain comprehension. The climate models specific to the terraforming process highlight another challenge. Stability. Earth's climate remains relatively stable due to complex feedback mechanisms that have evolved over billions of years. An engineered climate would need carefully designed stabilizing systems to prevent runaway warming or cooling. The simulation shows how engineered carbon sinks, managed cloud systems, and controlled ice cap regulation might work together to maintain habitable conditions on a transformed Kepler-22b. Transportation between Earth and a terraformed Kepler-22b represents a challenge of a completely different magnitude than the terraforming itself. At 620 light-years, the journey would require either near-light speed travel or generation ships where multiple human lifetimes pass during transit. The engineering concepts for such vessels appear on a dedicated screen, massive structures combining propulsion, habitat, and life support systems designed to function reliably for centuries. The room contains physical models of these hypothetical interstellar vessels, ranging from sleek matter-antimatter-powered craft designed to reach 10% of light speed to enormous habitat ships resembling small rotating worlds unto themselves. The contrast between these models highlights the fundamental trade-off. Faster ships require exponentially more energy, but allow single-generation journeys, while slower vessels can transport larger populations but require societies capable of maintaining purpose and function across multiple generations. Despite these extraordinary challenges, the terraforming scenarios presented in the laboratory share one common element. They all appear theoretically possible, given sufficient technological development, resource commitment, and time. No fundamental physical laws prevent humanity from transforming Kepler-22b into a habitable world, regardless of its starting conditions. The barriers are practical rather than theoretical, a matter of engineering scale, energy availability, and societal commitment. This theoretical possibility creates a powerful emotional response as you move through the laboratory. The models, simulations, and engineering concepts represent not just scientific speculation but a vision of humanity's potential future, a species capable of reshaping worlds circling distant stars to create new homes among the cosmos. The air seems to vibrate with the audacity of this vision, a dream that connects modern science to the most ancient human desires to explore and settle new frontiers. As the day in the planetary engineering laboratory draws to a close, the simulations continue running on their century-long time frames, showing the gradual transformation of a distant super-Earth from alien world to potential human habitat. The models spin slowly in their projected fields, representations of a planet humanity has never seen directly but might someday remake in Earth's image. The technical challenges remain sobering, the timescales humbling, but the possibility, however distant, of a terraformed Kepler-22b beckons from across 620 light-years of interstellar space. Distance shapes destiny. As you enter the Interstellar Propulsion Laboratory, the first visual that commands your attention is the scale model of our stellar neighborhood suspended from the ceiling. Earth appears as a tiny blue dot beside the glowing yellow sphere representing our Sun. Kepler-22 exists at the very edge of this three-dimensional map, almost brushing the ceiling 60 feet above, a small star with an even smaller point of light orbiting it. Kepler-22b. The physical separation between these two systems generates an immediate visceral understanding that no number alone can convey. The distance to Kepler-22b is approximately 3.6 times 10 to the 15th miles. Written in full, that's 3,600 trillion miles. The number exceeds human comprehension, existing in the realm of astronomical calculations rather than intuitive understanding. If you were to count one number per second without stopping, it would take over 114 million years to reach 3.6 times 10 to the 15th longer than mammals have existed on Earth. Light itself, traveling at 186,282 miles per second, requires 620 years to cross this gulf. Every observation we make of Kepler-22b shows not the planet as it exists today, but as it existed 6 centuries ago, when Joan of Arc was burned at the stake, when the Ming dynasty ruled China, when the Inca Empire was expanding across South America. This temporal disconnect creates a constant, sobering background to all interstellar planning. The propulsion systems laboratory occupies a cavernous space filled with prototype engines, fuel synthesis equipment, and massive computational arrays dedicated to solving the physics of interstellar travel. The air carries the scent of machine oil, ozone from electrical discharges, and the indefinable smell of metals under stress. The temperature varies noticeably as you move through different sections, from the cryogenic cooling areas to the plasma containment research zones. Each step through this facility reinforces the enormity of the challenge: how to cross a distance that light itself requires centuries to traverse. The fundamental challenge of interstellar travel can be expressed in a single equation displayed prominently on the main screen. E equals sign phi mu forward. Energy requirements scale with the square of velocity, creating exponential increases in the energy needed to approach significant fractions of light speed. The implications become immediately apparent when applied to even a modest interstellar mission. Accelerating a 1,000-ton spacecraft to just 10% of light speed would require energy equivalent to the entire annual electricity production of human civilization. Current chemical propulsion systems which powered humanity's ventures to the moon and robotic exploration of our solar system prove woefully inadequate for interstellar journeys. The exhaust velocity of chemical rockets tops out around 2.5 miles per second, less than 1/50,000th the speed of light. The rocket equation, also displayed on the laboratory screens, shows the brutal mathematics. Even using the most efficient chemical propellants and the lightest materials, a chemical rocket would need to be composed of 99.9999% fuel to achieve even a tiny fraction of light speed. The nuclear propulsion testing chamber, sealed behind multiple safety barriers, contains scale models of various advanced propulsion concepts. Nuclear fission rockets, which heat propellant using controlled nuclear reactions, could achieve exhaust velocities around 9 miles per second, a significant improvement over chemical systems but still far too slow for practical interstellar travel. The timeline calculations show a fission-powered spacecraft would require tens of thousands of years to reach the Kepler-22 system. Nuclear pulse propulsion, conceptualized in the Project Orion designs from the 1960s, offers more promise. This approach would use the energy of nuclear explosions directed against a massive pusher plate to propel a spacecraft. The theoretical maximum velocity approaches 3% of light speed, which would reduce travel time to Kepler-22b to approximately 20,000 years, still beyond the scope of a single human mission, but potentially within the range of multi-generational spacecraft or robotic precursors. The fusion propulsion development area showcases more advanced concepts. Nuclear fusion, which powers our sun and all stars, offers energy densities millions of times greater than chemical reactions. A deuterium-helium-3 fusion rocket could theoretically achieve 7 to 10% of light speed, reducing travel time to Kepler-22b to 6,000 to 9,000 years. The engineering models show massive magnetic nozzles containing fusion plasma at temperatures exceeding 100 million degrees, directing the energetic particles to generate thrust. Matter-antimatter annihilation represents the ultimate conventional propulsion technology. When matter and antimatter particles meet, they convert directly to energy following Einstein's famous equation E=mc². This perfect energy conversion could theoretically power spacecraft to velocities approaching 30 to 50% of light speed, bringing travel times to Kepler-22b down to 1,200 to 2,000 years. The antimatter production and containment systems required, however, extend far beyond current technology, with production rates millions of times higher than what CERN can currently achieve. The propulsion challenge scales directly with mission objectives. A small robotic probe weighing a few tons requires far less energy to accelerate than a habitat ship designed to transport a self-sustaining human population. The mission profiles displayed on the engineering screens show this trade-off explicitly. Smaller, faster probes could reach Kepler-22b sooner, while larger habitat ships with human passengers would require longer transit times using propulsion systems with lower acceleration but greater total impulse. Even with the most optimistic projections for propulsion technology, the journey to Kepler-22b remains a multi-generational undertaking. This creates unique challenges in spacecraft design well beyond propulsion. Life support systems must function reliably for centuries or millennia. Social structures must accommodate multiple generations born, living, and dying during the journey. Knowledge transfer systems must preserve the mission's purpose and technical capabilities across dozens of generations. The Habitat Design Laboratory adjacent to the Propulsion Center addresses these challenges. The models show self-contained ecological systems designed to recycle air, water, and nutrients with near-perfect efficiency. Unlike International Space Station systems with service lives measured in decades, these habitats would need to function autonomously for centuries, with the capacity for repair and renewal using only materials available on board. The scale of these habitat ships corresponds directly to mission duration and population requirements. A fast mission using matter-antimatter propulsion might require habitats supporting only a few hundred specialists for a millennium. A slower mission using more achievable fusion propulsion would need larger habitats supporting thousands of people for many millennia, essentially functioning as artificial worlds rather than mere vessels. Regardless of propulsion technology, the vast distances involved create unavoidable risks. The interstellar medium, while enormously less dense than the near vacuum within our solar system, still contains hydrogen atoms, dust particles, and occasional larger objects. At velocities approaching a significant fraction of light speed, impacts with even tiny particles release enormous energy. A single dust grain the size of a bacterium striking a spacecraft at 20% of light speed would hit with the energy of a hand grenade. The shielding laboratory demonstrates various approaches to this problem. Layered shields of advanced materials could absorb or deflect smaller particles. Active systems using electromagnetic fields might divert charged particles. More exotic concepts involve creating a bow wave of ionized particles ahead of the spacecraft to sweep the path clear. The most comprehensive protection, however, would likely come from redundancy, designing spacecraft with multiple independent modules, any of which could sustain the mission if others were damaged. Navigation across interstellar distances presents its own set of challenges. Unlike solar system missions where course corrections can be commanded from Earth with time delays measured in minutes or hours, an interstellar mission would need nearly complete autonomy. Radio signals from Earth to a spacecraft halfway to Kepler-22b would take 310 years to arrive, making real-time guidance impossible. The navigation systems under development rely on a combination of celestial reference points, onboard computational modeling, and autonomous decision-making. The star tracking devices in the laboratory can determine a spacecraft's position to extraordinary precision by measuring the apparent positions of multiple reference stars. Onboard gravity gradient sensors would detect subtle variations in the gravitational field as the spacecraft approaches the Kepler-22 system, allowing for increasingly precise navigation during the final approach phase. The sheer scale of the distance creates scenarios rarely considered in conventional spaceflight. A spacecraft traveling at 10% of light speed would cross the diameter of Earth's orbit around the Sun in just over 9 hours. At such velocities, the spacecraft would traverse the entire Kepler-22 system in a matter of days unless it decelerated, creating a daunting challenge for both deceleration systems and observation equipment designed to study the target planet. Deceleration represents a propulsion challenge equal to or greater than initial acceleration. While solar sails might harness radiation pressure for braking when approaching a stellar system, most propulsion systems would need to carry fuel for both acceleration and deceleration phases, effectively doubling the already enormous energy requirements. The mission profiles on display show various solutions, from magnetic sails that could interact with the stellar wind of Kepler-22 to staged propulsion systems that jettison components after the acceleration phase. Time dilation, a consequence of Einstein's special relativity, offers a slight reduction in subjective travel time for the fastest mission profiles. At 50% of light speed, time on board the spacecraft would pass approximately 15% slower than for observers on Earth. While far from the dramatic time compression portrayed in science fiction, this effect would reduce a 1,200-year journey to approximately 1,020 years from the perspective of the travelers, a modest but real benefit for multi-generational missions. The economic calculations for interstellar missions to Kepler-22b defy conventional analysis. The development costs for advanced propulsion alone would likely exceed the entire global economy for multiple years. The resources required to build habitat ships capable of supporting human populations for millennia would dwarf the largest engineering projects in human history. The screen displaying the economic model simply shows beyond conventional economic frameworks requires civilization-scale commitment. This civilization-scale commitment raises profound questions about motivation and purpose. Why would humanity invest such enormous resources in reaching a single planet 620 light-years away? The sociological research displayed in an adjacent section explores various potential drivers: existential risk mitigation through species diversification, resource acquisition from multiple star systems, scientific knowledge advancement, or the fundamental human drive to explore and expand beyond current boundaries. The timeline for actual mission capability depends on technological development rates that remain highly uncertain. The most optimistic projections suggest small robotic probes using nuclear pulse propulsion might be technically feasible within the next century, though still requiring unprecedented resource commitments. Human missions using more advanced propulsion could follow in subsequent centuries. The full colonization potential of Kepler-22b, if it proves suitable, might not be realized for a millennium or more. This extended time frame creates a profound disconnect between those who might initiate interstellar programs and those who would see them completed. The philosophical implications fill screens in the long-term planning section. The multi-generational nature of both development and execution requires institutional structures capable of maintaining focus and commitment across centuries, a challenge perhaps even greater than the technical obstacles. As the day in the propulsion laboratory progresses, engineers conduct a test firing of a prototype plasma engine. The controlled discharge illuminates the test chamber with an eerie blue glow, the superheated exhaust reaching temperatures comparable to the surface of a star. The system achieves an exhaust velocity of approximately 93 miles per second, remarkable by the standards of current spacecraft, but still just 1/2000th the speed of light. The test serves as a visceral reminder of how far current technology remains from the capabilities required for practical interstellar travel. The laboratory contains a special visualization room where the full scale of the challenge becomes experientially apparent. As you enter this darkened space, pinpoints of light represent stars at their correct relative positions and distances. Earth's sun glows near your feet, while Kepler-22 appears as a dim point near the far wall, 620 light-years distant at the room's scale. The vast emptiness between these points drives home the fundamental reality of interstellar travel. The distances involved are so immense that they render conventional transportation concepts essentially meaningless. Yet, despite these overwhelming challenges, the research continues. Each incremental advance in propulsion efficiency, materials science, artificial intelligence, or life support technology brings the possibility of reaching Kepler-22b marginally closer. The laboratory embodies both the sobering reality of the difficulties and the persistent human determination to overcome them. The air seems to vibrate with this tension between the nearly impossible and the theoretically achievable. As you prepare to leave the propulsion laboratory at day's end, your attention is drawn to one final display, a historical timeline of transportation technology. It shows how human mobility has increased from walking speed to supersonic flight in just a few centuries, from the first tentative steps beyond Earth's atmosphere to robots exploring the outer solar system in less than a century. The exponential curve suggests that while interstellar travel to systems like Kepler-22b remains beyond our current capabilities, the trajectory of human technological development makes it difficult to definitively declare it forever impossible. What remains certain is that the 3,600 trillion miles separating Earth from Kepler-22b represents more than just a physical distance. It defines the scale of one of humanity's greatest potential challenges, a journey that would require not just revolutionary technology, but a transformation in how we conceptualize time, resources, and our place in the cosmos. Every calculation, every prototype, every simulation in this laboratory exists in the shadow of that vast gulf of space, a distance so enormous it can never be truly conquered, only respected, accommodated, and perhaps someday traversed. Communication defines civilization. The ability to share information across distance and time separates humanity from all other Earth species. As you enter the Deep Space Communications Laboratory, the first thing you notice is the absolute silence. The room is acoustically isolated. Its walls lined with anodized radio-absorbent material that creates a dead zone free from electromagnetic interference. This quiet space serves as the testing ground for technologies designed to bridge the greatest communication gap humanity has ever contemplated, the 620 light-year distance to Kepler-22b. The central display shows a simple but sobering timeline. A radio message sent today to Kepler-22b would arrive in the year 2645. Any reply transmitted immediately would return to Earth in the year 3265. This 1,240-year round-trip time represents the fundamental, immutable constraint imposed by the speed of light. No technological advancement, no clever coding scheme, no quantum breakthrough can overcome this basic limitation of physics. This communication delay transforms the very nature of what contact might mean. The screen transitions to show a historical analogy. Imagine European explorers in the 15th century dispatching a message that would only be received by their distant descendants, with replies coming back to people who would have no direct connection to those who sent the original communications. The vast temporal gulf creates a discontinuity unlike anything in human experience. The Atmospheric Effects Laboratory demonstrates another critical challenge for interstellar communication. Any signal transmitted from Earth must first penetrate our own atmosphere, which absorbs or reflects electromagnetic radiation at many wavelengths. The display shows the atmospheric transmission windows, specific frequency ranges where radiation passes through relatively unimpeded. Radio waves between approximately 1 and 10 GHz can pass through Earth's atmosphere with minimal attenuation, as can certain bands of infrared, visible light, and some ultraviolet frequencies. These transmission windows define the practical options for interstellar communication. The equipment around you represents different approaches to the challenge. Radio frequency transmitters, designed to operate at the sweet spot of hydrogen's 21 cm emission line, stand alongside optical communication systems using powerful lasers. Each offers different trade-offs in terms of power requirements, beam divergence, and potential for detection at interstellar distances. Signal attenuation over distance follows the inverse square law, displayed prominently on one of the main screens. At twice the distance, signal strength drops to 1/4. At 10 times the distance to 1/100th. By the time a signal travels 620 light-years, its intensity has diminished by a factor of 1.5 times 10 to the 38th power. This staggering attenuation means that a powerful transmission from Earth would be almost undetectably faint by the time it reached the Kepler-22 system. The power requirements to overcome this attenuation appear on adjacent displays. To achieve a detectable signal at Kepler-22b using current radio telescope technology, a transmitter would need power measured in gigawatts, comparable to the output of major power plants, focused precisely toward the target star for extended periods. The engineering challenges of generating, directing, and sustaining such powerful transmissions extend well beyond current capabilities. Optical communication using lasers offers some advantages in terms of beam collimation and energy efficiency. The laser testing chamber contains prototype systems capable of maintaining beam coherence over simulated extreme distances. Even with these advanced systems, the beam width at Kepler-22b would span millions of miles due to the unavoidable effects of diffraction, requiring precise targeting and enormous receiving apertures to capture the attenuated signal. The signal-to-noise ratio represents perhaps the most fundamental challenge in interstellar communication. The galaxy itself generates background radiation across the electromagnetic spectrum, from the cosmic microwave background to the radio emissions of stars, pulsars, and other natural phenomena. Any artificial signal must be distinguishable from this natural background to be detected. The signal processing screens show how advanced algorithms attempt to extract meaningful patterns from simulated noise, using techniques that push the boundaries of information theory. Encoding information for interstellar transmission raises unique challenges in data density and error correction. The Information Theory Laboratory contains systems developing maximally compressed encoding schemes, methods to pack the greatest possible meaning into the minimum number of bits. Adjacent displays show the robust error correction codes needed to ensure that message integrity survives the inevitable corruption introduced by interstellar medium interference and quantum noise effects. What information would be most valuable to transmit across such vast distances? The content development section addresses this profound question, categorizing knowledge into tiers of importance. Scientific principles, mathematical constants, and physical laws occupy the highest priority level, as they provide the foundation for all other knowledge. Technological information, biological data, and cultural context follow in descending priority, reflecting difficult choices about what aspects of human civilization could or should be preserved in an interstellar message. The temporal relevance of information creates another layer of complexity. Knowledge transmitted today would take 620 years to reach Kepler-22b. By then, much of our current scientific understanding and technology might be obsolete. The content development algorithms attempt to identify knowledge with timeless value, principles and discoveries likely to remain relevant regardless of technological advancement in the intervening centuries. Language itself presents a fundamental communication barrier. How can we ensure that beings with potentially different sensory systems, cognitive structures, and evolutionary histories could interpret our messages? The linguistic encoding laboratory approaches this challenge through mathematics and physics as universal languages. The displays show message structures beginning with simple counting principles and physical constants, gradually building to more complex concepts using these foundational elements as reference points. The directed energy facility adjacent to the main laboratory houses the prototype transmitters for interstellar communication. These massive devices represent the current state-of-the-art in high-power narrow-beam transmission. Even so, the capacity calculator shows their limitations clearly, using the most efficient encoding schemes and the full bandwidth of these advanced transmitters. Sending the text equivalent of a basic encyclopedia to Kepler-22b would require approximately 15 years of continuous transmission. If humans ever establish a presence in the Kepler-22 system, communication with Earth would be limited not just by time delay, but by bandwidth constraints. The available data rate might allow for basic text messages and simple images, but high-definition video or immersive data would require transmission times measured in decades or centuries. This constraint would fundamentally alter the relationship between a potential colony and Earth, forcing a level of independence unlike any frontier settlement in human history. The temporal implications extend beyond the practical to the philosophical. The screens in the long-term planning section explore how communication across 620 light-years would affect human conceptions of time, continuity, and purpose. Messages sent might be intended for descendants dozens of generations removed, requiring content of sufficient value to justify preservation and transmission across such timescales. The reception equipment for interstellar signals presents challenges as significant as transmission. The laboratory contains models of advanced receiving systems designed to capture and process the extraordinarily faint signals that might arrive from distant civilizations. These include massive phased array designs spanning thousands of square miles, space-based interferometers with baselines measured in astronomical units, and quantum-enhanced detectors operating at the theoretical limits of sensitivity. Signal verification protocols occupy another section of the laboratory. How would we distinguish a genuine artificial signal from natural phenomena or instrumentation artifacts? The methodology displayed shows multiple independent verification steps: detection by different instrument types, confirmation of non-natural patterns, and extended observation to verify consistency. The threshold for declaring a confirmed communication from Kepler-22b would require evidence far exceeding that needed for conventional scientific discoveries, reflecting the extraordinary nature of such a claim. The interstellar medium itself creates additional communication challenges. The space between star systems, while incredibly sparse by terrestrial standards, still contains enough hydrogen atoms, dust particles, and ionized gas to affect electromagnetic transmissions over such vast distances. The simulations show how these materials can cause signal dispersion, frequency shifting, and scintillation effects, essentially a form of cosmic static that further complicates the detection of already faint signals. Quantum effects introduce another layer of complexity. At the quantum level, even empty space experiences fluctuations in energy that can affect the propagation of electromagnetic signals. Over interstellar distances, these quantum fluctuations become significant enough to require consideration in communication system design. The Quantum Information Laboratory develops error correction techniques and encoding methods specifically designed to address these fundamental physical limitations. The possibility of using other communication methods beyond electromagnetic radiation occupies a specialized research area. Neutrino communications, gravitational wave signals, or quantum entanglement effects all receive theoretical consideration, though each presents even greater technical challenges than conventional electromagnetic transmission. The displays show the theoretical advantages each might offer. Neutrinos pass through matter with minimal interaction. Gravitational waves are essentially unaffected by the interstellar medium. Entangled particles might theoretically allow instantaneous correlation across any distance, alongside the enormous practical difficulties in generating and detecting such signals. The communication challenges scale with the potential for human presence at Kepler-22b. A small robotic probe with limited objectives might require only occasional, low-bandwidth communication with Earth. A self-sustaining human colony would initially need more substantial information exchange, though this requirement would likely diminish as the colony developed independent knowledge and capabilities. The mission profile screens show these different communication requirement trajectories, from short scientific missions to permanent settlement scenarios. For any human mission to Kepler-22b, onboard data storage becomes crucial given the communication constraints. The Information Preservation Laboratory develops systems capable of maintaining data integrity for centuries or millennia without degradation. These range from advanced digital storage with multiple redundancy to more exotic approaches like molecular storage in engineered DNA or quantum states preserved in specially designed crystal lattices. The psychological impact of communication delays represents another research focus. How would humans react to the knowledge that any message sent would not receive a reply within their lifetime? Studies displayed on the psychology screen suggest this communication reality would fundamentally alter human relationships and organizational structures, potentially creating entirely new social dynamics focused on extremely long-term continuity and purpose. For any permanent settlement at Kepler-22b, the communication delay would eventually necessitate complete autonomy. The colony development simulations show how initially dependent outposts would be forced to develop independent capabilities across all domains: technological, scientific, medical, social, and philosophical. The 620-year one-way delay makes any form of guidance, governance, or assistance from Earth effectively meaningless for real-time challenges. This inevitable autonomy raises profound questions about human identity and civilization. Would a colony at Kepler-22b, separated by such vast communicative distance, eventually develop a distinct culture, language, and identity? The sociological models suggest that within a few generations, significant divergence would be inevitable. Within a dozen generations, still less time than a single round-trip communication, the colony might consider itself an entirely separate branch of humanity. As the day in the communications laboratory continues, technicians conduct tests on prototype high-power transmitters. The directed energy beam, invisible but powerful enough to be felt as warmth on your skin, if not for the safety shields, represents the cutting edge of current technology. Yet even this advanced system would produce a signal at Kepler-22b barely distinguishable from background noise without receiving equipment far more sensitive than anything currently existing. The fundamental asymmetry between transmitting and receiving creates strategic communication questions addressed in another research section. Given the enormous power requirements and technical challenges of transmission, some researchers advocate for a listening strategy rather than active messaging. The possibility of establishing communication relays represents a potential long-term solution to the delay problem. The mission architecture screens show concepts for networks of automated communication stations positioned at intervals between Earth and the Kepler-22 system. While still bound by light speed limitations, such a network could maintain continuous information flow, with each node receiving, storing, and retransmitting data to bridge the vast distance in more manageable segments. The scale models of these hypothetical relay stations show self-sustaining systems with nuclear or antimatter power sources, massive transmission and reception antennas, and autonomous maintenance capabilities designed to function reliably for centuries without human intervention. Their deployment would itself represent an interstellar mission of unprecedented scope, requiring technologies well beyond current capabilities, but potentially achievable as stepping stones toward full human missions to distant star systems. As the day draws to a close, the Communications Laboratory continues its fundamental work on what might be humanity's greatest informational challenge, bridging a gap where a message takes longer to arrive than the entire history of the United States, where a response would not return until a time as distant from us as we are from the fall of the Roman Empire. The silence of the laboratory seems to underscore the profound quiet of interstellar space, a silence that humanity's most advanced technology still struggles to breach across the 620 light-years to Kepler-22b. Scientific revolutions often emerge from unexpected sources. As you step into the multidisciplinary innovation laboratory, the first thing you notice are the walls lined with digital displays tracking research breakthroughs spawned by Kepler-22b studies. What began as a focused investigation of a single exoplanet has blossomed into a catalyst for advances across dozens of scientific disciplines. The air feels charged with intellectual energy, scientists from seemingly unrelated fields conversing animatedly in clusters throughout the open workspace. The temperature hovers at precisely 71 degrees Fahrenheit, calibrated for optimal cognitive function during extended research sessions. The story of how Kepler-22b transformed science begins with fundamental advances in observational astronomy. The initial detection of this distant world pushed the limits of photometric precision, requiring instruments capable of detecting brightness variations of just 0.00029%. The technology developed to achieve this sensitivity now appears on the instrumentation wall. New generations of photodetectors with quantum efficiencies approaching 100%, optical systems that can maintain nanometer-level stability across temperature gradients, and algorithmic innovations that can extract meaningful signals from what once would have been considered noise. These advances in sensitivity quickly found applications beyond astronomy. The medical imaging section displays how similar photometric techniques now allow detection of subtle changes in tissue reflectivity, revealing early-stage cancers long before they become visible through conventional methods. You can almost feel the weight of this unexpected connection, how the search for a distant world has created tools that now save human lives daily. The prototype scanner hums quietly in its testing chamber, its internal components directly descended from technologies first developed to find planets like Kepler-22b. Spectroscopic analysis underwent a similar revolution. The challenge of detecting atmospheric components around a planet 620 light-years away required fundamentally new approaches to separating weak spectral signatures from background noise. The spectroscopy laboratory contains systems capable of detecting single molecules in complex mixtures, identifying isotopic ratios with unprecedented precision, and characterizing materials based on subtle absorption features. These spectroscopic breakthroughs transformed environmental monitoring on Earth. The screens show global networks of sensors using Kepler-derived techniques to track pollutants at concentrations once thought impossible to detect, map carbon dioxide with meter-level precision, and identify industrial emissions from specific sources. What began as a quest to understand a distant atmosphere has become an essential tool for protecting our own. The materials science section showcases another unexpected spin-off from Kepler-22b research. The need to model potential super-Earth conditions, pressures and temperatures far exceeding those naturally occurring on Earth led to new simulation techniques and eventually to laboratory methods for creating and studying materials under extreme conditions. The high-pressure diamond anvil cells, plasma deposition systems and quantum material simulators all trace their lineage to questions first raised about the possible composition of Kepler-22b. These materials research capabilities have yielded practical applications displayed around the laboratory: superconducting materials that operate at room temperature, ultra-strong lightweight alloys used in next-generation transportation systems, and quantum materials with properties that seemed theoretically impossible just decades ago. A sample case contains a small disk of metallic hydrogen, a material that exists naturally only in the cores of gas giants, now synthesized in laboratories using techniques developed to understand super-Earth interiors. Computational modeling experienced perhaps the most dramatic acceleration. The challenge of simulating the complex, interacting systems of a planetary body from core dynamics to atmospheric chemistry to potential hydrological cycles required new approaches to multi-scale multi-physics modeling. The computational cluster occupying one corner of the laboratory represents the latest generation of these systems, capable of simulating planetary processes across 27 orders of magnitude in both time and space scales. These computational advances transformed fields far beyond planetary science. The medical research displays show how similar modeling techniques now simulate human physiological systems with unprecedented fidelity, allowing pharmaceutical development without animal testing, personalized medicine tailored to individual genetic profiles, and predictive models for disease progression that guide preventative treatments. The economic value of these computational breakthroughs alone has exceeded the entire cost of the original Kepler mission by a factor of several thousand. Biological research demonstrates some of the most unexpected connections to Kepler-22b studies. The question of what forms life might take on a super-Earth environment led to fundamental reconsiderations of the boundaries of biochemistry. The astrobiology section contains experimental systems exploring alternative biochemistries, organisms engineered to use different solvents than water, metabolic pathways utilizing atmospheric compositions unlike Earth's, and synthetic biology systems designed to function under elevated gravitational conditions. These investigations into the extremes of possible biology yielded insights into life's fundamental mechanisms. The displays show how researchers identified core biochemical principles that transcend the specific chemistry of Earth life, developed new theories of abiogenesis applicable across different planetary environments, and created synthetic biological systems with capabilities beyond anything found in nature. Each discovery traces back to questions first raised about the potential for life on Kepler-22b. The practical applications of this expanded biological understanding appear in adjacent sections: engineered microorganisms that can remediate environmental contaminants previously considered permanent, medical treatments based on alternative metabolic pathways discovered through exobiology research, and agriculture systems designed to function in environments once thought hostile to food production. The sweet, slightly earthy scent of an experimental algae bioreactor fills this section of the laboratory, a tangible reminder of how abstract questions about distant worlds can yield concrete benefits for humanity. Communications technology experienced revolutionary advances, driven by the challenge of potential interstellar contact. The quest to develop systems capable of transmitting or receiving signals across 620 light-years drove innovations in signal processing, error correction, and information density. The communications research area contains prototype systems that approach the theoretical limits of data transmission efficiency, encoding information at densities that would have seemed impossible a generation ago. These communication breakthroughs transform terrestrial information systems. The displays show how error correction codes developed for interstellar communication now secure quantum computing networks, how compression algorithms designed to maximize information density in interstellar messages have revolutionized data storage, and how signal processing techniques created to extract meanings from noise-dominated channels now allow communication in previously impossible environments, from deep underwater to inside nuclear reactors. Energy research followed a similar trajectory of unexpected advancement. The enormous energy requirements for potential interstellar missions drove investigations into power generation, storage, and transmission well beyond conventional approaches. The Energy Systems Laboratory contains prototypes that push theoretical limits: room temperature superconductors that allow lossless power transmission, quantum vacuum energy extraction devices that tap the zero-point field, and compact fusion systems that approach the energy density of antimatter reactions. While full interstellar capability remains distant, these energy technologies have transformed terrestrial power systems. The displays show how fusion research accelerated by decades, how grid-scale energy storage became economically viable through technologies first conceived for interstellar missions, and how distributed power generation achieved efficiencies once thought physically impossible. The quiet hum of a prototype quantum energy system provides background ambience to this section of the laboratory, a sound representing a fundamental breakthrough in humanity's relationship with energy. Propulsion technology, perhaps predictably, experienced some of the most dramatic advances. The challenge of traversing interstellar distances crystallized the limitations of conventional propulsion with unprecedented clarity, driving research into fundamentally new approaches. The propulsion test chamber contains scaled prototypes representing these new directions: magneto-hydrodynamic systems that can achieve exhaust velocities approaching 1% of light speed, quantum vacuum plasma thrusters that interact directly with the structure of space-time, and fusion-driven systems with thrust-to-weight ratios exceeding anything in conventional rocketry. These propulsion breakthroughs found immediate applications in near-Earth space and terrestrial transportation. The screens show how access to orbit decreased in cost by orders of magnitude, how travel times within our solar system dropped from years to weeks, and how even ground transportation was transformed by technologies first developed with Kepler-22b in mind. The low, resonant vibration occasionally felt through the laboratory floor comes from a propulsion system test chamber several levels below, physical evidence of how theoretical questions about reaching a distant super-Earth have yielded tangible transportation capabilities here on Earth. Artificial intelligence research accelerated dramatically through Kepler-22b studies. The requirement for systems capable of making complex autonomous decisions over the timescales involved in interstellar missions drove the development of AI architectures with unprecedented capabilities for long-term planning, self-modification, and operation without human oversight. The AI Research Center contains systems that represent a qualitative break from previous approaches, demonstrating not just faster processing but fundamentally different approaches to cognition, learning, and decision-making. These AI advances transformed disciplines from medicine to infrastructure management to scientific research itself. The displays show how diagnostic systems now consistently outperform human physicians across all specialties, how urban management systems coordinate resources with an efficiency that has eliminated scarcity in many regions, and how scientific discovery is increasingly driven by AI systems capable of generating and testing hypotheses at scales impossible for human researchers alone. The subtle changes in lighting and environmental conditions as you move through the laboratory reflect the operation of one such system, continuously optimizing the research environment based on demonstrated cognitive performance metrics. Materials engineering for extreme environments represents another field transformed by Kepler-22b research. The need to model and potentially survive conditions on a super-Earth with higher gravity, different atmospheric chemistry, and potentially more extreme weather drove the development of materials with unprecedented properties. The materials testing chamber contains samples that demonstrate these advances: metamaterials with negative refractive indices, programmable matter that can reconfigure its properties in response to environmental conditions, and structural materials with strength-to-weight ratios approaching theoretical limits. These materials advances quickly found Earth-based applications. The displays show how buildings now withstand earthquakes and hurricanes that would have destroyed conventional structures, how medical implants incorporate materials that seamlessly interface with biological systems, and how electronics now operate reliably in environments from Arctic cold to volcanic heat. A sample case contains a small piece of transparent material that feels cool to the touch despite being heated to several hundred degrees, a tangible example of how research driven by questions about a distant world has created seemingly impossible materials here on Earth. Psychological research experienced unexpected acceleration through Kepler-22b studies. The question of how humans might adapt to life on a super-Earth with different gravity, day length, and sensory environment led to fundamental reconsiderations of human cognitive and psychological adaptability. The cognitive science section contains experimental setups investigating these questions, virtual reality systems that simulate alien environments, longitudinal studies of psychological adaptation to altered physical parameters, and research into human performance under conditions unlike any naturally occurring on Earth. These psychological investigations yielded insights that transformed mental health treatment, education, and human performance optimization. The displays show how treatments for previously intractable psychological conditions achieved breakthrough results using principles discovered through exoplanetary adaptation research, how educational methods incorporate findings about cognitive flexibility to accelerate learning across all disciplines, and how human performance in extreme Earth environments has reached levels once thought physiologically impossible. Social science research followed a similar trajectory of unexpected advancement. The question of how human societies might function during interstellar journeys or on distant worlds led to fundamental reconsiderations of social organization, governance, and cultural evolution. The Sociological Research Center contains simulations exploring these questions, models of social structures designed to maintain stability over multi-generational timescales, governance systems capable of adapting to radically changed environments, and cultural transmission mechanisms designed to preserve crucial knowledge across centuries. These sociological insights found immediate applications in addressing Earth's most pressing social challenges. The displays show how conflict resolution mechanisms derived from long-term space mission planning now successfully mediate previously intractable conflicts, how resource management systems designed for closed-loop habitats have transformed sustainability practices on Earth, and how education systems based on multi-generational knowledge transmission principles have dramatically improved intergenerational equity and cooperation. Perhaps most profoundly, philosophy and ethics experienced revolutionary developments through engagement with Kepler-22b research. Questions about humanity's relationship with environments beyond Earth, our responsibilities to potential indigenous life forms, and the implications of becoming a multi-stellar species drove fundamental reconsiderations of value systems, ethical frameworks, and the meaning of human civilization itself. The Philosophy Center contains ongoing discussions of these questions, with contributions from diverse cultural, disciplinary, and ideological perspectives. These philosophical inquiries yielded new frameworks for addressing Earth's ethical challenges. The displays show how environmental ethics has been transformed by principles first developed for potential exoplanet stewardship, how questions of justice and fairness have found new resolutions through frameworks designed for multi-generational equity in interstellar missions, and how the fundamental question of humanity's purpose has found new approaches through consideration of our potential role as a species capable of extending life beyond its planet of origin. As the day in the Multidisciplinary Innovation Laboratory progresses, researchers continue their work across these diverse fields. The constant cross-fertilization of ideas, physicists consulting with biologists, engineers working alongside philosophers, computer scientists collaborating with sociologists, creates an intellectual environment unlike traditional academic departments. What binds these disparate disciplines together is the common source of their inspiration. Questions first raised by the discovery of a single planet, Kepler-22b, orbiting a sun-like star 620 light-years from Earth. The scientific journals displayed on digital screens around the laboratory tell the statistical story of this intellectual explosion. Research papers referencing Kepler-22b have been cited over 300,000 times across more than 60 distinct disciplines. The economic impact assessment shows spin-off technologies valued at more than $15 trillion. The educational statistics reveal how Kepler-22b has become one of the most powerful recruiting tools for bringing students into scientific careers. A distant world sparking curiosity that leads to engagement with all fields of science. What began as an astronomical discovery has become a lens through which humanity has examined its own capabilities, challenges, and potential futures. As you prepare to leave the laboratory at day's end, the final display summarizes the most profound impact of Kepler-22b research. It has provided a focal point for human intellectual endeavor that transcends traditional boundaries between disciplines, between nations, between theoretical and applied research. The search to understand a world so distant we might never reach it has transformed how we understand and inhabit the world directly beneath our feet. The question of whether humanity should attempt to colonize Kepler-22b transcends science and engineering to touch our deepest values and vision of the future. As you enter the colonization ethics complex, the atmosphere feels different from the technical laboratories you've visited previously. The lighting mimics natural sunlight, plants grow in hydroponic columns throughout the space, and the walls display rotating artwork depicting humanity's relationship with nature across different cultures and eras. This environment is designed to encourage integrative thinking across disciplines, science and art, technology and ethics, practical logistics and philosophical purpose. The central holographic display shows various possible futures for Kepler-22b and humanity's relationship with it. In one scenario, self-replicating robotic probes establish an observation network around the planet, studying it for centuries without direct human presence. In another, a small research outpost houses rotating teams of scientists who conduct studies while minimizing their environmental impact. A third shows a large-scale colonization effort, with millions of humans establishing a permanent civilization adapted to Kepler-22b's conditions. Each scenario comes with its own technological requirements, timeframes, and profound ethical implications. The foundational ethical question appears prominently on the main discussion board. Do we have the right to extend human presence to other potentially habitable worlds? The positions articulated represent a spectrum of perspectives from across human cultures, religions, and philosophical traditions. Some argue that humanity has a cosmic purpose to spread life and consciousness throughout the universe. Others contend that preservation and non-interference should be our guiding principles when approaching worlds that may harbor their own evolutionary paths. The first major ethical consideration involves the possibility of indigenous life. The Xenobiology Research Center contains models of potential detection systems designed to identify life forms that might be entirely unlike Earth biology. The methodologies range from searching for chemical disequilibrium that would indicate biological processes to identifying patterns of energy usage that would suggest metabolism. The ethical frameworks displayed alongside these technologies emphasize that any detection of indigenous life from simple microbes to complex organisms would fundamentally transform our relationship with Kepler-22b. The Prime Directive protocols appear on adjacent screens, detailed guidelines for how humanity would limit its presence and impact if life were discovered. These range from complete non-interference to carefully controlled observation, depending on the nature and complexity of any life forms detected. The room contains simulation spaces where researchers work through scenarios involving different types of potential indigenous biology, developing ethical response frameworks for each possibility. The scent of soil and growing things permeates this section of the complex, a deliberate design choice to keep researchers connected to the foundational importance of life as they contemplate these profound questions. Your fingers brush against the leaves of a plant as you move through the space, a tangible reminder of the biological heritage that we might someday transport across interstellar distances or encounter in alien forms around distant suns. If Kepler-22b proves lifeless, different ethical questions emerge. The environmental ethics displays show competing viewpoints on humanity's relationship with uninhabited but pristine worlds. Some perspectives advocate for preservation of natural states, viewing planets as having intrinsic value beyond human utility. Others present a stewardship model where careful human presence could enhance planetary development. Still others propose maximal utilization, arguing that lifeless worlds represent resources for humanity's expansion and development. The tensions between these perspectives become apparent in the colonization architecture models throughout the complex. Some designs show minimal impact research stations that would leave the planet largely untouched. Others display terraforming projects that would gradually transform Kepler-22b to more closely match Earth conditions. The most ambitious show planet-wide development with urban centers, transportation networks, and industrial facilities utilizing local resources. Each approach comes with visualizations of its long-term impact on Kepler-22b's environment. The simulations run across centuries and millennia, showing how different human choices would shape the future of this distant world. The progression created by these models generates a visceral response, a sense of responsibility for outcomes that would unfold long after our own lifetimes. The weight of these potential futures seems to physically press upon you as you watch landscapes transform across simulated eons. The question of who should decide humanity's approach to Kepler-22b occupies another major section of the ethics complex. The governance models on display range from extensions of current international space law to entirely new frameworks designed specifically for interstellar colonization. Some propose that decisions should remain Earth-based, with representative bodies including diverse human perspectives. Others suggest that only those who would actually travel to Kepler-22b should have decision-making authority over its future. The temporal disconnect between Earth and any Kepler-22b mission complicates these governance questions. Given the centuries-long travel times and communication delays measured in millennia, any colony would inevitably develop independence from Earth. The socio-political simulations show how different initial governance structures might evolve over generations, some maintaining connections to founding principles while others diverge dramatically as new cultural forms emerge in response to Kepler-22b's unique environment. The psychological research area explores the human dimensions of potential colonization. Studies displayed on the screens examine the psychological profiles that might predispose individuals to succeed in interstellar colonization, the group dynamics that would support multi-generational missions, and the cultural adaptations that would help humanity thrive in an environment fundamentally different from our evolutionary home. What emerges from these psychological studies is the portrait of a cosmic human, an individual or community adapted for life beyond Earth, not just physiologically but psychologically and culturally. The displays show how such adaptation might manifest greater comfort with extended timeframes, stronger communal bonds balanced with psychological resilience and cognitive flexibility that allows adaptation to environments unlike anything in human evolutionary history. The genetic considerations of long-term colonization occupy a specialized research area. The displays show models of how human physiology might need to adapt to Kepler-22b's higher gravity, different atmospheric composition, or altered radiation environment. Some approaches involve technological mitigations, exoskeletons, enclosed habitats, or medical interventions. Others consider the potential role of genetic adaptation, either through selection over generations or through direct engineering of colonist genomes to better suit the target environment. The ethical questions surrounding genetic modification for colonization appear on adjacent displays. Different cultural and religious perspectives on human genetic engineering are presented alongside practical considerations about consent across generations and the potential creation of human subspecies adapted to different worlds. The weight of these considerations feels almost tangible as you move through this section, questions that touch the very definition of humanity and our future as a species. Resource utilization ethics forms another major focus area. The economic models show different approaches to Kepler-22b's potential resources, from minimal extraction focused only on colony survival to large-scale industrial development, utilizing the planet's geological assets. The sustainability frameworks attached to each model demonstrate their long-term implications, from approaches designed to last millennia, with minimal impact, to those that would fundamentally transform the planet's geology and chemistry within a few centuries. These resource considerations connect directly to the question of what a successful colony would look like. The various visions displayed range from small, self-sufficient outposts focused on research to extensive civilizations with populations in the millions. Some models prioritize minimal environmental footprint. Others emphasize human thriving and expansion. Still others seek a carefully calculated balance between human needs and planetary preservation. The question of whether colonization should be seen as a response to existential threats on Earth receives focused attention in another section. The risk assessment displays show projections of various catastrophic scenarios that might threaten human civilization on our home planet, from asteroid impacts to pandemics to environmental collapse. The ethical frameworks examine whether such risks justify investment in interstellar colonization as a form of species-level insurance policy, or whether resources would be better directed toward addressing Earth's challenges directly. This existential calculus creates some of the most challenging ethical questions in the entire complex. If humanity faces potential extinction on Earth, does this create a moral imperative to establish colonies elsewhere, regardless of cost or impact on destination worlds? Or does it instead create an obligation to focus all resources on preserving our original planetary home? The philosophical positions articulated represent fundamentally different visions of humanity's relationship with Earth and the cosmos. The question of who would go to Kepler-22b generates particularly intense ethical debate. The selection criteria models show different approaches to choosing potential colonists, from technical skills and genetic factors to psychological profiles and cultural diversity. The justice considerations explore whether colonization opportunities should be distributed according to merit, representational diversity, lottery systems, or other allocation principles. The funding models examine who would bear the enormous costs of such missions and whether this creates implicit rights to determine who participates. The intergenerational ethics section addresses perhaps the most profound question of all. What obligations do we have to the unborn generations who would live and die during transit to Kepler-22b or as part of an established colony? The consent frameworks grapple with the fact that most humans involved in a multi-generational mission would never have chosen to participate. They would simply be born into it. The cultural transmission models explore how founding values and knowledge would be preserved or transformed across generations of colonists. This temporal dimension of colonization ethics becomes particularly apparent in the mission design displays. Some approaches prioritize fast transit using advanced propulsion, minimizing the number of generations that would live and die in transit. Others accept longer time frames but provide more robust habitat ships with greater resources for intermediate generations. The trade-offs involve not just technical factors but profound value judgments about the quality of life for people who would exist solely as links in a chain connecting Earth to an eventual colony. The religious and spiritual perspectives on colonization occupy a dedicated contemplation space. The displays show how different faith traditions view humanity's relationship with the cosmos, from those that see universe-wide human expansion as fulfilling divine purpose to those that emphasize humanity's responsibility as caretakers rather than conquerors. The space includes symbols and wisdom from dozens of spiritual traditions, acknowledging that decisions about interstellar colonization would touch the deepest human questions about purpose, meaning, and our place in creation. As day transitions toward evening in the ethics complex, a community discussion begins in the central forum. Philosophers, scientists, engineers, artists, religious leaders and policy specialists gather to debate these interconnected questions. The conversation flows across disciplinary boundaries, each perspective illuminating different dimensions of potential human engagement with Kepler-22b. The air feels charged with the significance of these exchanges, discussions that might someday shape decisions affecting not just the future of a distant planet, but humanity's role in the cosmos. The practical near-term recommendations emerging from these ongoing deliberations appear on the action boards. They emphasize continued observation and study of Kepler-22b, development of detection methods that could identify potential indigenous life from Earth, and establishment of international frameworks for decision-making about interstellar exploration and potential colonization. These modest first steps acknowledge both the enormous technical challenges involved in reaching Kepler-22b and the profound ethical questions that must be addressed before humanity commits to any specific path forward. Beyond these procedural recommendations, the value statements displayed throughout the complex articulate principles that might guide humanity's relationship with Kepler-22b, regardless of the specific technical approaches adopted. They emphasize humility in the face of cosmic scales, respect for life in all its forms, commitment to sustainability across generations, and recognition that human expansion beyond Earth should enhance rather than diminish our ethical development as a species. What becomes clear as you move through this complex is that Kepler-22b represents more than just a distant super-Earth with potential for habitability. It serves as a mirror reflecting humanity's deepest questions about our purpose and place in the universe. The decisions we might someday make about this world would reveal not just our technological capabilities but our values, wisdom, and vision of what human civilization should become. As you prepare to leave the ethics complex at day's end, the final display reminds visitors that while Kepler-22b orbits a star 620 light-years distant, the questions it raises exist here and now on Earth. How we approach this distant world with wisdom or recklessness, humility or arrogance, preservation or exploitation, will be determined not by future generations but by foundational choices made in our time. The air seems to vibrate with the weight of this responsibility as you step back into the evening, looking up towards stars that hold worlds we are only beginning to understand, much less contemplate reaching. In the soft darkness, one particular star, too faint to see with the naked eye, but precisely located in the constellation Cygnus, holds special significance. Around it orbits Kepler-22b, a world that has catalyzed scientific breakthroughs, philosophical inquiry, and a deeper recognition of both human potential and human responsibility. Whether humanity ever reaches this distant super-Earth matters less than how the journey toward understanding it transforms us, scientifically, technologically, and most importantly, ethically. The greatest distance to be crossed is not the 620 light-years of physical space, but the gap between what we are and what we might become, a species worthy of reaching toward the stars.